To build Have Blue, we needed $10 million. One can't imagine what goes through your mind when you have to ask the board of directors to invest $10 million at a time when the corporation was considering declaring bankruptcy. The $10 million investment brought the company several billion dollars of sales and a reputation of technical superiority and stealth technology. The advantages of low observables, or stealth technology, have been a military matter of considerable interest for decades. Applicable not only to aircraft, but to all other forms of military equipment as well. Attempts to camouflage or reduce the visibility of hardware and personnel have been ongoing since the beginning of recorded military history. During World War II, the application of camouflage paint patterns was studied with considerable intensity. Scientifically conducted research helped generate patterns that genuinely reduced an aircraft's visibility both in the air and on the ground. Polished aluminum, for instance, was criticized for its notable ability to reflect sunlight and increase the detection distance of a target aircraft. Dull, non-glare matte-type paints eliminated the problem, but not without increased expense and some cost in performance. The exigencies of war curtailed extensive research into the development of airworthy, non-radar reflective structural materials, but some attempts were nevertheless made. The Germans, in particular, placed emphasis on lowering the radar return of select aircraft, including the notable O-229. This extremely advanced all-wing jet fighter, built primarily of wood over a steel tube load-bearing structure, in some production models was to have utilized a wood sandwich ply with a core material of granulated charcoal. Presumed to have absorbed radar energy, the charcoal was calculated to reduce the aircraft's radar return by a not insignificant margin. The war ended before the technology could be fully exploited. Countermeasures were slow to develop initially, with little focus on reducing radar visibility or countering radar energy during the 1950s and 1960s. It wasn't until the Vietnam War that effective electronic countermeasures were pursued. The threat of radar-guided missiles required a reassessment of technology, leading to the development of ECM pods and chaff dispensers. Lockheed gained experience in anti-radar features through programs like the U-2, A-12, and SR-71. In 1974, DARPA requested studies for a low observable fighter, excluding Lockheed, but they were eventually included through the Skunk Works efforts. Lockheed refined external shaping techniques using Echo 1, a computer program predicting radar cross-sections, or RCS, based on mathematical formulas. They employed faceting, creating a three-dimensional aircraft from flat panels to reduce RCS. Validation testing was conducted with a model called the Hopeless Diamond, demonstrating lower RCS than previous designs. In August of 1975, Lockheed, along with Boeing and Northrop, received invitations from the Defense Advanced Research Projects Agency to participate in a highly competitive project known as the Experimental Stealth Test Bed. The objective of this project was to develop and test an innovative aircraft design with exceptional low observability characteristics. After a thorough evaluation process, Lockheed was selected in April 1976 to proceed with the detailed design, development, and testing of the aircraft, which was named Have Blue. A single-seat subsonic aircraft featured a distinctive design aimed at achieving both high maneuverability and low observability. A significant feature of the aircraft was the inclusion of a large two-position flap known as the platypus, which automatically deflected downward when the angle of attack exceeded 12 degrees, enhancing the nose-down pitch control. The initial engine runs were accomplished on the first Have Blue aircraft on November 4, 1977, at Lockheed's Burbank facility. In order to maintain security, the aircraft was parked between two semi-tractor trailers over which a camouflage net had been installed. On December 1, 1977, with Lockheed test pilot Bill Park at the controls, Have Blue lifted into the air. A new era in military aviation had just begun. Only 20 months had passed since contract award. As previously noted, the primary objective of the test program was to demonstrate VLO technology. Towards this end, Have Blue 1001 would demonstrate loads flutter, performance handling qualities, and stability and control. Have Blue 1002 was designated as the PCS test vehicle. Have Blue 1001 accomplished 36 flights over the next 5 months and successfully expanded the flight envelope sufficiently to allow the RCS testing to be performed. Have Blue 1002 joined the program during 1978 and flew for the first time on July 20th with Air Force pilot Norman Ken Dyson at the controls. This aircraft differed from Have Blue 1001 in that it possessed a real airspeed system and did not have a drag chute installed. It also incorporated nose wheel steering to improve ground handling and was adorned with all the coatings and materials required to perform its intended task. Following some airspeed calibration flights, the aircraft accomplished 52 flights during the next 12 months and completed the low observable testing. The final phase of testing in a simulated integrated air defense environment was completed during July of 1979. The aircraft demonstrated its low observable capabilities against ground and airborne systems during these tests. Its low acoustic signature was also verified. The Have Blue program was a low-cost demonstration of a radically new concept in VLO aircraft design. Have Blue program accomplishments included, from a technical standpoint, lowest RCS aircraft in the world by several orders of magnitude, VLO infrared signature, VLO visual signatures, VLO acoustic signature, and confirmation of complex aerodynamics. In conclusion, it was determined VLO tactical and strategic aircraft could be designed, produced, and operated.
I always felt it would perform very well, but I never expected it to perform as well as it did. We had not involved the airplane operationally, and therefore the operators didn't know how to use the airplane. It's like having a new tool. I was worried we hadn't operated it enough.
On the evening of January 16th, 1991, television viewers who tuned into CNN witnessed a rare live preview of future wars. Correspondents Bernard Shaw and Peter Arnett, broadcasting from the room in Baghdad's Al-Rashid Hotel, reported on Iraq's state of alert under Saddam Hussein.
This is, something is happening outside. Peter Arnett joined me here. Let's describe to our viewers what we're seeing. The skies over Baghdad have been illuminated. We're seeing bright flashes going off all over the sky. Peter?
Well, there's anti-aircraft gunfire going into the sky. However, we have not yet heard the sound of bombs landing, but there's tremendous lightning in the sky.
I have a sense, Peter, that people are shooting towards the sky, and they are not aware or cannot see what they're shooting at. This is extraordinary. We're getting starbursts, seeming starbursts in the black sky. We have not heard any jet planes yet, Peter.
No plane. Now the sirens are sounding for the first time. The Iraqis have informed us.
5.5 months after Iraq invaded Kuwait and 17 hours past the coalition's withdrawal deadline, Baghdad was shielded by the world's densest air defenses.
This included 76 surface-to-air missile launchers, or SAMs, and nearly 3,000 anti-aircraft artillery guns. Iraqi radar operators scanned the moonless sky for signs of incoming aircraft, but saw nothing. Shaw remarked, "We haven't heard any planes yet," speculating if the B-52 bombers flew too high to detect. 650 miles to the south, at Khamis Musheit, in southwestern Saudi Arabia, U.S. Air Force pilots of the 37th Tactical Fighter Wing were also glued to CNN's broadcast. 2 hours earlier, some of their squadron members had taken off from King Khalid Air Base for the war's first airstrike. One of their objectives, located on the west bank of the Tigris River, was the 370-foot Al-Kark communications tower, which transmitted CNN's signal to the outside world. As the estimated time of the strike neared, everyone at King Khalid kept one eye on CNN and one on their watch, counting down. If all went as planned, the network would go dark. Now. The need for an aircraft capable of penetrating modern air defense systems had actually emerged from another Middle Eastern conflict almost 20 years prior. During the 1973 Yom Kippur War, Israeli-flown McDonnell Douglas F-4 Phantoms were heavily impacted by Egypt's radar-guided SA-6 SAMs. At the same time, in Vietnam, the U.S. Air Force was dedicating more than half its aircraft to radar suppression instead of bombing. The first real solution to these challenges came in 1975 from the most likely source, Lockheed California's Advanced Projects Division, the renowned Skunk Works. Engineers there realized that curved surfaces reflect energy in multiple directions, like how a soap bubble reflects sunlight. However, if an aircraft had flat surfaces, like the facets of a diamond, reflections could be directed away from the enemy receivers. Faceting led to handling difficulties for pilots, prompting Skunk Works team leader Ben R. Rich to secure government funding for 2 full-sized prototypes under the purposely vague codename Have Blue. Because the aircraft provided near immunity to radar, the Air Force quickly funded the production of full-scale development, or FSD, models. The new design incorporated lessons from the Have Blue program, including increased engine power. The inlets and exhausts were baffled and soundproofed. Reducing noise instead of the typical jet turbine roar, the plane emitted a high-pitched whine that could set dogs barking before it even appeared. The inward-canted fins of the prototypes had reflected heat emissions, so the FSD models featured outward-canted fins in a V-shaped butterfly tail. Combat requirements modified by the need for stealth influenced the rest of the redesign. Unlike most military aircraft since the 1950s, the plane carried no radar, as even an inactive radar acts as a reflector. Even the standard radio antennas found on conventional aircraft were designed to retract beneath the plane's surface when not in use. Additionally, since external fuel tanks and weapons would negatively impact the plane's radar cross-section, or RCS, all fuel and munitions were stored internally. Over the next decade, the stealth fighter, as it was popularly known, became a major topic of discussion in the aviation world. The new aircraft was assigned the code name Senior Trend and the misleading designation F-117. Test flights were mostly conducted at night, scheduled to avoid detection by Soviet reconnaissance satellites. The Nellis Range, also home to the Air Force's Red Flag air combat exercises involving American and Allied military aircraft, maintained a security screen to keep the other aircraft away from the Groom area. Despite the F-117 being 33% larger than the prototype, its radar cross-section, or RCS, measured between 0.01 and 0.001 square meters, roughly equivalent to that of a small bird.
This allowed the F-117 to approach ground-based search radars 90% closer and airborne radars 98% closer before detection. Testing was still ongoing when the Air Force ordered a full wing of the production version of Senior Trend, designated the F-117A Nighthawk. The first military pilot to fly a Nighthawk was Lieutenant Colonel Alton C. Whitley, a Vietnam veteran with combat experience in the A-7 and North American F-100, and a former commander of the Air Force's Aggressor Squadron. He recalled, "When I first looked at the F-117A, it reminded me of some Star Wars type of aircraft. I thought, boy, is this the 21st century?" Normally, the Nighthawk's fly-by-wire system managed its instability so well that when one jet lost an entire rudder at high speed, the pilot only learned of it from the chase plane, yet landed safely. With low wing loading and G-limits comparable to the F-4, the F-117 reportedly handles well. The wildly publicized nickname Wobbly Goblin stems from its departure characteristics. Once it loses control, recovery is nearly impossible. In June 1986, and again in October 1987, Nighthawks crashed into the ground due to pilot fatigue and disorientation. Despite efforts by the U.S. Air Force to keep these incidents under wraps, news leaked out. In November 1988, the Pentagon publicly disclosed a grainy, retouched photo that revealed very little of the F-117. Twice, stealth fighters were on the verge of bombing targets in Libya, but the missions were canceled to maintain secrecy. It wasn't until December 1989, during Operation Just Cause, the U.S. invasion of Panama, that the F-117A saw its first combat. During the operation, 6 Nighthawks flew to Panama via Texas and the Caribbean Sea, with 2 serving as backup aircraft and turning back unneeded. 2 others were assigned to support special forces attempting to capture General Manuel Noriega, but that mission was canceled. Confusion over a last-minute change led to a mix-up regarding the remaining target, a barracks housing 2 battalions of elite enemy troops. The goal was to stun rather than kill. The lead F-117A achieved this with a single 2,000-pound Mark 84 bomb. Known colloquially as the Hammer, the bomb, capable of a lethal radius of 400 feet and blowing out eardrums half a mile away, exploded in a field beside the barracks, causing significant confusion among the Panamanians. The second stealth jet also hit its target, although it was the wrong location. Nonetheless, the Air Force deemed the mission successful, as the stealth jets remained undetected by Panamanian radar. On August 17, 1990, Colonel Al Whitley took command of the 37th Tactical Fighter Wing. 4 hours later, he recalls, "The word came in to deploy our first squadron. The U.S. and its allies planned to remove Saddam Hussein's forces from Kuwait. King Khalid Air Base, located 6,500 feet up in the mountains near the Red Sea and nicknamed Tonopah East, had been constructed in the late 1970s in exchange for delivering McDonnell Douglas F-15 Eagles and AWACS airborne radars to Saudi Arabia. Because the base was beyond the range of Iraqi Scud-B missiles, the stealth jets required 3 mid-air refuelings to reach their primary target, downtown Baghdad. "I generally put the F-117s against the Baghdad targets," said the Air Force's Chief Mission Planner, Brigadier General Buster C. Glosson, where we would have lost conventional airplanes. The mission team included only 3 combat veterans, Whitley, his deputy commander, and 1 pilot from Operation Just Cause. However, after 5 months of intense training over the barren Nevada desert, the Night Stalkers and Ghost Riders were ready. They carried 2 tons of bombs, each over more than 1,000 miles of desert at night, shortly before 3 a.m. local time on January 17, 1991. 8 stealth jets arrived above Baghdad with lights off and radio silent. Captain Marcel Kerr-David was tasked with bombing the Al-Kark Tower. Even though I felt very well prepared with my training, I was somewhat apprehensive about the aircraft. He later admitted. Its stealthiness had not been tested in combat, and everyone wondered whether or not this stealth stuff really worked. Does the U.S. military have a new black aircraft program in development? Since the mid-1980s, the aviation press has been scrutinizing Pentagon documents and eyewitness accounts, suggesting a new stealth fighter for the next century. In February 1985, the Pentagon budget request accidentally listed a project alongside Lockheed's SR-71 Blackbird and U-2 spy planes, under the code name Aurora. This may have been a ruse similar to the F-19 ploy, as Aurora was also a name for a maritime patrol aircraft developed for the Canadian military. However, while the Canadians received their Auroras, the Pentagon's Aurora project reportedly continued, with funding rising from $80 million in fiscal 1986 to approximately $2.3 billion by 1987. Typically, the Air Force had no comment on the matter. However, by 1988, it was rumored to be working on a replacement for its SR-71 reconnaissance aircraft, which it retired with surprising eagerness in March 1990. Artistic renderings, some perhaps intentionally misleading, depict super blackbirds weighing over 150 tons, powered by variable cycle turbo ram rockets burning liquid methane or hydrogen, cruising the edge of space at Mach 6. Eyewitness accounts suggest that Aurora, if it exists, is more modest in size, but not necessarily in performance. In early 1990, Aviation Week and Space Technology reported unusually loud nighttime air traffic over Edwards Air Force Base in California, with one source describing the noise as the sky being ripped open. In June 1991, a sonic boom similar to those produced by space shuttles re-entering the atmosphere and strong enough to be detected by seismographs rumbled across Southern California. Judging by its sonic footprints, the object was flying toward the vast Nellis Air Force Range at speeds exceeding Mach 3. Activity seems to be concentrated around the remote Machrihanish Air Base in western Scotland, which was linked to the F-117A before the Nighthawk was publicly known. In November 1991, a Royal Air Force air traffic controller reportedly saw a radar blip leave Machrihanish traveling at Mach 3. Additionally, in August 1989, an engineer on an oil rig in the North Sea witnessed a mid-air refueling operation involving a mysterious aircraft shaped like an isosceles triangle when viewed from below. One thing is certain: design teams like the Skunk Works are always pushing the boundaries of innovation. Anticipating a barrage of anti-aircraft fire, mission planners assigned a second stealth jet to mark Kerr-David's target and reduce his workload. As the laser beam illuminated the dome-shaped roof of the Al-Kark, a forward-looking infrared radar, or FLIR scope, in Kerr-David's plane detected the signal and displayed it on the cockpit's 8-inch video screen. Using a fingertip control on his throttle stick, Kerr-David locked his aim point onto the laser reflection, and his weapons system projected an imaginary basket above it, guiding where the bomb needed to be dropped for a successful strike. 10 seconds before release, Kerr-David pressed the pickle button to activate his weapons system. The Nighthawk's bomb bay doors opened, and its lethal payload, a 1-ton GBU-27AB guided bomb, specifically designed for the F-117A, was released into the slipstream. With the threat of anti-aircraft fire mitigated, David, who was later awarded the Silver Star for his action, dropped his bomb from a relatively high altitude and close to the Alcarc. He then veered north towards his secondary target, a command bunker in the Taji suburbs. Meanwhile, the second F-117 remained on station briefly, using its belly-mounted downward-looking infrared radar, or DLIR, laser designator, to mark the target for David's bomb as it descended. In their room at the Al Rashid Hotel, CNN reporters picked up the sound of an air raid warning. "Now the sirens are sounding for the first time," Peter Arnett noted. "The Iraqis have informed us." At that moment, as if from nowhere, David's GBU-27 struck the Alcarc Tower, drilling halfway down before detonating. The building split in half, an event missed by CNN viewers and personnel at King Khalid as the network immediately went offline. An audio-only land link allowed Peter Arnett to describe the blinding spray of aimless return fire rising above the Baghdad skyline, while the Iraqi gunners' radars showed no aircraft above them. Seconds later, another F-117A's GBU-27 hit directly across the Tigris from the Alcarc. It penetrated the roof of the 12-story Baghdad International Telephone Exchange, known to Air Force mission planners as the AT&T building, the only target in the city scheduled for a double hit. Major Jerry Leatherman of the 415th Tactical Fighter Squadron, one of those planners, circled in from the northeast 60 seconds after the first strike. He dropped 2 high-blast Mk-84 bombs from 3 miles up through the hole in the building's roof. The first bomb landed slightly low, but the second hit perfectly, together demolishing the top 4 floors. In rapid succession, 3 waves of stealth jets struck their targets with a precision that was both merciful and ruthless, targeting the Iraqi Air Force and Ba'ath Party headquarters, Air Defense Control Centers, Rashid Airfield, and other high-value objectives, including 2 of Saddam Hussein's presidential palaces. Within half an hour of the initial strikes, Baghdad went dark, likely due to the destruction of the power grid rather than Iraqi countermeasures. Despite the blackout, the city remained illuminated by the persistent anti-aircraft fire. Back at King Khalid, ground crews anxiously counted the returning aircraft, with the last arriving only after dawn. Remarkably, every Nighthawk returned safely without a single scratch. In the first 24 hours of the war, the 42 stealth fighters at King Khalid, just 2.5% of the total Allied aircraft deployed in the Gulf, were responsible for 31% of the targets attacked. Damage estimates were lower than anticipated, partly due to a low mist obscuring Baghdad at dawn. Additionally, the cloud cover, which was 3 times the seasonal average during the war, not only interfered with subsequent operations, but also compromised the jet's stealth capabilities. "If you're just above a cloud deck with the moon reflecting off it, you can really stick out," explained Leatherman. At one point, an F-117A was shadowed by what seemed to be an Iraqi Dassault Mirage F-1 fighter, which was shining a landing light or spotlight to visually acquire the stealth jet. A slight maneuver, however, broke the lock, making it the closest any Nighthawk came to a dogfight over Iraq. Throughout the Gulf War, the Black Jets were consistently tasked with the most perilous, high-priority targets. These included radar sites, SAM and Scud launchers, enemy command control communications facilities, bridges, hardened aircraft shelters, and bunkers. Their data recorders captured some dramatic video footage for Air Force publicists. Notable examples include a hardened Scud storage facility destroyed by a laser-guided bomb dropping through an air duct, a bomb blowing in the door of an ammunition bunker followed by another bomb exploding inside, and a GBU-27 descending an elevator shaft to detonate deep within the Iraqi Air Force headquarters, demolishing all 4 walls. Ultimately, the F-117A Nighthawk's precision strikes played a crucial role in minimizing collateral damage and saving lives on both sides during the Gulf War. By successfully handling more than 40% of the coalition force's strategic targets, the Nighthawks demonstrated the effectiveness of stealth technology and precision bombing. The success of the F-117A led to significant changes in U.S. Air Force tactics and technology post-war. The 37th Tactical Fighter Wing, redesignated the 49th Tactical Fighter Wing, relocated from Tonopah to Holloman Air Force Base, New Mexico. Air Force analysts have so far found no way stealth technology can be compromised in the foreseeable future. In any case, the F-117A Nighthawk, the Skunk Works, and Ben Rich are assured their places in aviation history. We guaranteed to deliver an aircraft which would have stealth characteristics, be virtually undetectable by today's known radar technologies, and be able to deliver a weapons system with unprecedented accuracy, said Rich. We've done that. Our accomplishments speak for themselves. In many ways, the F-22 Advanced Tactical Fighter is the true daughter of the F-117. Stealth will be a major factor in the USA remaining a superpower in the 21st century. We worked very hard with the F-22 to integrate stealth into a supersonic, supermaneuverable fighter, and we succeeded. After our last day of YF-22A flight demonstrations from Edwards late on December 28, 1990, I said to my wife, Judia, we won. And we did. Our team delivered results. It was a privilege to lead this team. The F-22 Raptor is the most advanced aircraft of its kind, designed around the principles of first look, first shot, first kill. It is set to become the primary air superiority fighter for the U.S. Air Force in the 21st century. The Raptor, as its name suggests, is a lethal machine. As menacing as it appears, it is even more deadly when deployed for its missions. Deadly and undetectable from long distances. This stunning fifth-generation fighter combines unparalleled dogfighting abilities with precise ground attack capabilities. Confidence in these objectives stems from a synergistic blend of features and capabilities, including stealth technology, the ability to cruise at supersonic speeds over long distances without afterburners, and an integrated, highly sophisticated avionics suite. The FA-22A has been designed to be more maneuverable, better armed, more reliable, easier to maintain, more readily supportable, and more capable in air-to-ground missions than any other comparable aircraft in history. Throughout the 1960s and 70s, the Soviets developed various missiles to attack at different altitude bands, making it impossible to fly under or over the missile threat. You had to confront it directly. One way to address this was to prioritize the suppression of enemy air defenses, specifically by destroying missile sites and their radars as the most crucial mission for the Air Force. By the 1970s, air superiority had once again become a top priority, leading the U.S. Air Force to commit to building its first pure air superiority fighter, which would eventually become the F-15 Eagle.
I have never seen a finer joint government-industry team that's organized with the technical competence to carry out the job that's been assigned to them, or to do it in a manner of close-knit teamwork.
However, just as the F-15s became operational in 1978, alarming new evidence suggested that their superiority might be short-lived. At the same time, and perhaps most importantly, reconnaissance satellites photographed several new fighter prototypes, the Mikoyan MiG-29 and Sukhoi T-10, at the Ramenskoye Flight Test Center near Zhukovsky, about 40 miles southeast of Moscow. The new generation represented a significant improvement in capability over anything previously observed by U.S. intelligence services. It was clear to everyone involved that a new air-to-air combat platform would be necessary to counter the threat posed by these new Russian aircraft. The Sukhoi T-10 was a huge shock to Western analysts. It was larger than the F-15 and far bigger than any previous Soviet-built fighter. If the MiG-29 had already concerned the American military establishment, the existence of the Sukhoi T-10 set off alarm bells. These aircraft were highly advanced, capable of competing with some of the top NATO fighters like the Phantom and ultimately the F-15. Just weeks into his first term, America's 40th president increased U.S. defense spending by $32.5 billion, initiating a massive rearmament of the United States.
I mentioned earlier, it is absolutely essential that we increase our spending for national defense if we're to preserve the peace.
In 1981, the Cold War was heating up. As Reagan and Brezhnev faced off, the U.S. Air Force concluded that it urgently needed a replacement for its F-15, an advanced tactical fighter, or ATF, that would have no equal. As American planners began developing the concept of air-land battle to prepare for a potential World War III, the U.S. Air Force started considering the type of equipment it would need for such a conflict. On August 24, 1982, a Program Management Directive, or PMD, was issued, changing the program element's name from Combat Aircraft Technology to Advanced Tactical Fighter. Concurrently, two sub-projects were established under this banner: the Advanced Tactical Fighter, which included concept and technology development, 7 airframe companies: Boeing, General Dynamics, Grumman, Lockheed, McDonnell Douglas, Northrop, and Rockwell. Each received $1 million concept development investigation contracts. And the Joint Fighter Engine, an engine technology demonstration program managed jointly with the U.S. Navy. Pratt & Whitney and General Electric each received contracts valued at $202 million in September 1983. Other companies contending for the contract included Allison, Garrett, and Teledyne CAE. The 7 competing companies submitted a total of 19 conceptual designs, ranging from Northrop's lightweight cooperative fighter, smaller than an F-16, to Lockheed's battlecruiser, based on the design of their short-lived YF-12A long-range interceptor. Additionally, an in-house design, a subsonic low observable fighter, was submitted by the Air Force's Flight Dynamics Laboratory, or AFFDL. Of the approximately 19 studies submitted, 4 were eventually chosen to represent different mission philosophies: a very light, austere, low-cost design, a supersonic cruise and maneuver design, a subsonic, low observable design, and a high Mach, high-altitude design. From these, it was concluded that the ideal air-to-air platform would combine low observability with super cruise and superior maneuverability. The platform would, in turn, offer reduced vulnerability to surface-to-air missiles, while nearly eliminating exposure to anti-aircraft, artillery, and other short-range systems. The Red Baron study, which analyzed air-to-air combat in Vietnam, had sparked the race for stealth technology. An operational analysis of the Vietnam War showed that most aircraft were shot down by enemy aircraft they had not seen. This highlighted the significant advantage of being undetected in air combat. Air combat data from World War II and Korea reinforced the need for invisibility. The principle of stealth technology is to make an airplane virtually invisible to the enemy. An aircraft's shape must reflect incoming radio waves away from enemy radar rather than towards it. To further enhance low observable characteristics, an airplane is covered in materials that absorb radar signals, further reducing its visibility on a radar screen. Leading the way in stealth technology was Lockheed Skunk Works. In 1977, amid unprecedented security, Lockheed had flown a prototype of the world's first stealth fighter. By the 1980s, during Operation Just Cause, its F-117 had helped to dismantle General Noriega's regime in Panama. Now, the U.S. Air Force decided that any new fighter must incorporate stealth technology and identified two other areas in which a future air superiority fighter should excel. The challenge was issued, and it was up to the finest aviation manufacturers in the world to respond. The Advanced Tactical Fighter program was about to begin, and the Raptor, America's fifth-generation fighter, was about to be hatched. By 1983, U.S.-Soviet relations had reached a new low. Following Leonid Brezhnev's death, the Politburo, now controlled by former KGB boss Yuri Andropov, was labeled by Reagan as the focus of evil in the modern world. Continuing his policy of rearmament, Reagan announced plans for the Strategic Defense Initiative, better known as Star Wars, prompting a furious reaction from Moscow. In August, when Korean Airlines Flight 007 on its way to Seoul from New York strayed several hundred miles off course into Soviet airspace, Russia responded. A fighter was dispatched, and the civilian airliner with 269 people on board was shot down. The shooting down of KAL-007 sent shockwaves around the world, straining international relations to the breaking point. Reagan's reaction to the crisis strengthened U.S. conviction that stealth would now be the prime requirement for America's new fighter.
I'd like to talk for a moment about why we're developing a new fighter at this time. There's probably not a person in this room or in the reach of your television cameras who isn't aware of the contribution of stealth to our success in Desert Storm. In that case, it was a bombing capability that we were seeing in action. But the principle will apply to both ground attack and air-to-air missions in the future. The ATF is intended to replace the aging F-15 Eagle, currently our frontline fighter. The Air Force's F-15s are outstanding aircraft, and they swept the skies in Desert Storm. However, when the ATF is first deployed, the F-15s will be over 25 years old. Several other aircraft, including some we faced in Desert Storm, are aerodynamically competitive today with the F-15 and other leading U.S. fighters. We win today with an edge in avionics and by relying on the superior skill and training of our pilots. Others will try to close that gap between now and the year 2002, when the first ATF squadron is fielded. The ATF will balance stealth, supercruise, and advanced avionics in a highly maneuverable fighter that will ensure that our pilots get first look and first kill. Thus, the ATF will ensure American air superiority well into the next century. As we have seen in Desert Storm, air superiority is essential to effective air and ground operations. American ground forces have not had to fight without air superiority since 1942, and we plan to keep it that way as well.
Following 4 initial drafts, the basic framework for the ATF requirement was released to the industry. The framework called for a radius of action of approximately 800 miles, supersonic cruise capability of 1.4 to 1.5 Mach, a 2,000-foot runway requirement, a gross takeoff weight of 50,000 pounds, and a unit cost of no more than $40 million in 1985 dollars. Importantly, the proposal implied that the ATF life cycle cost, or LCC, the aircraft unit cost upon delivery plus the cost of all spares, fuel, maintenance, and flying, should be at least as good as, if not better than, the McDonnell Douglas F-15. it was concluded that the submissions from Lockheed and Northrop were superior to those from Boeing, General Dynamics, and McDonnell Douglas. Each manufacturer would submit a design for the demonstration evaluation, or DEMVAL competition, with the understanding that the winning company would be the prime contractor, and its partners would be subcontracted to produce major components. Lockheed, whose initial design studies had been considered frontrunners during the early ATF reviews, had begun consortium discussions with Boeing and General Dynamics as early as June 1986. A public announcement was made on July 2nd, but did not formalize an agreement with its partners until the following October 13th. Consequently, Lockheed assigned Sherman Mullins as general manager for the ATF Team Program Office. Mullen would lead Lockheed in the prime contractor role, leveraging the unique technical strengths of Boeing and General Dynamics. 2 weeks later, Northrop followed suit by leading a team with McDonnell Douglas. In response to these teaming decisions, revised proposals from all 7 airframe contractors were submitted on July 28, 1986. By default, the 2 consortia were selected on October 31, 1986, to build 2 prototypes each for the revised demonstration and validation phase. Lockheed, under a $691 million contract, would build 2 of what later became its Model 1132, initially referred to as Configuration 092, under the official Air Force designation YF-22. Northrop, under a similar $691 million contract, would build 2 of its N-14 proposal under the official Air Force designation YF-23. At the end of the process, one of these designs would become America's new advanced tactical fighter. Costing billions of dollars, the new fighter aimed to make a significant technological leap into the 21st century. Just 9 months after being selected to build the demonstration and validation fighters for the U.S. Air Force, Lockheed shocked everyone by scrapping its original design. In a hectic 3-month process, with help from its partners, Lockheed produced a completely different configuration featuring a clipped delta wing. Over the next 4 years, at a cost of just over $2 billion, America's tactical fighter competition became the largest program of its kind. In 1990, just months after the disintegration of the Soviet Union, the shapes of the 2 rival designs were finally unveiled. Northrop's version, called the YF-23, closely resembled its original design. In contrast, Lockheed's design, called YF-22, appeared surprisingly conventional, featuring 4 tail surfaces, vectored thrust, a broad solid body, and a conventional wing. Unlike Lockheed's other stealth aircraft, the F-117, radar-absorbent materials were not applied over the entire FA-22, but used selectively on its edges, cavities, and critical surface areas. The F-22 carries its weapons internally. 4 weapons bays are hidden in the central mid-body section. 6 missiles can be carried in the ventral bays, which are covered with bifold doors. The side bays each hold 1 Sidewinder missile on a trapeze launcher. The mid-body section also houses the fighter's landing gear and complex inlet ducts. Attached to the mid-body is the forebody, which accommodates the cockpit and advanced avionics. Both the YF-23 and the YF-22 are impressive-looking machines, but their performance still needs to be tested. The most crucial stage of the competition is still to come: the flight testing. Northrop was first in the air. In August 1990, flown by Paul Metz, the YF-23 got airborne. The test was a huge success, but Lockheed was quick to respond. On September 29th, at Edwards Air Force Base in California, Lockheed Chief Test Pilot Dave Ferguson prepared the Raptor for its maiden flight. Over the next 3 months, the Raptor underwent a series of rigorous tests. The Air Force required both teams to provide performance projections, which would then be compared with the actual performance of the airplanes in various conditions, including subsonic and supersonic flight at different altitudes. The winner of this stage would earn a contract for 650 aircraft. The decision would hinge not just on what the contractors promised, but on the Air Force's confidence in their ability to deliver. During flight testing, the Raptor outperformed the Northrop YF-23 in several crucial performance areas. The YF-22 had clearly demonstrated that in every category it was far superior to any existing fighter. But it would be events in 1991 that would carve out the Raptor's future.
Two aircraft you see here, or you've seen in action in the flying prototypes, I think are an excellent demonstration of exactly what we were trying to accomplish with this demonstration validation front end and the prototyping and hardware demonstration, including the avionics test beds that went along with that. We ended up with two aircraft, each one of which could meet the Air Force's technical specifications and technical requirements. And that's why, as I said in the formal remarks, that we had here a set of proposals or a set of contract options, any one of which was in the acceptable range and any one of which could have been selected. So we were dealing with shades of differences, given that all of the proposals were in the acceptable range. We had to make the evaluation based on the criteria that were called out in the RFP, and we've done that, and the best I can do for you today is to report the final judgment of that process.
22 minutes after midnight on January 17, 1991, Lockheed's stealth F-117 spearheaded U.S. strikes against Saddam Hussein's regime. The performance of Lockheed's stealth bombers during Operation Desert Storm gave the company and its aircraft priceless publicity. However, another aircraft also emerged from the Gulf War with a glowing reputation. The F-15, the aircraft destined to be replaced by the ATF, emphatically confirmed its status as the foremost air superiority fighter in the world. Now it appeared that the need for an advanced stealth fighter, the F-22, might be unfounded. But not everyone agreed. By April 1991, bogged down by the F-15 debate, the U.S. Air Force prepared to announce the winner of the Advanced Tactical Fighter contract. Would the Raptor emerge from the controversy unscathed? After the DEM-VAL flight tests of the prototypes, Secretary of the Air Force Donald Rice announced that the Lockheed team and Pratt & Whitney were the winners of the ATF and engine competitions.
The DEM-VAL phase has accomplished the risk reduction and the design trade-offs that are its purpose. Its success is demonstrable in the excellent performance of the prototypes and the quality of the proposals from the contractor teams. To ensure the fairest possible evaluation of these outstanding designs and development teams, the evaluation process that we've been through has been intensive, thorough, and professional. That evaluation was conducted by Air Force and Navy teams, by a team involving both Air Force and Navy personnel, included not only the developer community, but users, testers, contracts experts, cost analysts, and all who would be involved in the next phase of development. The success of the demonstration validation phase and this formal evaluation process is also demonstrated by the fact that the evaluators were able to bring to me as the source selection authority 4 awardable contracts, each of which represented acceptable proposals that met Air Force requirements. However, in evaluating the engine and airframe proposals, one combination clearly offered better capability with lower cost, thereby providing the Air Force with a true best value. With all that said, I now announce that the ATF team will be composed of the Pratt & Whitney company who designed the F-119 engine, which will be integrated into the F-22, designed by Lockheed, teamed with Boeing and General Dynamics.
The YF-23 design was considered stealthier and faster, while the YF-22, with its thrust vectoring nozzles, was more maneuverable, as well as less expensive and risky. Having won the contract, Lockheed announced that it would locate the F-22's headquarters in Georgia, where the Raptor's forward fuselage would be built. General Dynamics would construct the F-22's mid-body section in Fort Worth, Texas, and Boeing would manufacture the wings and tail in Seattle, Washington. Follow-on work with the aircraft took place at Edwards Air Force Base, involving an additional 100 hours of flying time, approximately 25 flights, to expand the YF-22A's flight envelope and explore specific segments in greater detail. However, on April 25, 1992, the program encountered its first major setback. During preliminary testing, a YF-22, flown by Tom Morgenfeld, crashed shortly after takeoff. The aircraft hit the runway with the landing gear retracted, skidded approximately 8,000 feet, and caught fire. A key element of the Raptor's design, thrust vectoring, uses movable exhaust nozzles to adjust the angle of thrust from the two Pratt & Whitney engines. As the Raptor made its low-level flyby, Tom Morgenfeld kept the stick forward to keep the nose down. However, as the landing gear was retracted, the thrust vectoring engaged, pushing the aircraft towards the tarmac. The pilot struggled to correct this sudden change in direction as the Raptor began to veer off course. Despite the loss of the stealth aircraft, the program had achieved its major goals. 10 million man-hours of analysis, 4,000 hours of radar testing, and hundreds of hours of flight testing had gone into the aircraft's development, even before construction began. In fact, the F-22 had undergone more flight testing than any other fighter before full-scale production. On April 9th, the first F-22A, officially named Raptor, an earlier attempt to name the aircraft Superstar failed in 1991, was unveiled in a public ceremony at Lockheed Martin's Marietta, Georgia facility. Air Force pilots would soon have the opportunity to evaluate the new aircraft themselves. First flown by the Air Force in 1997, pilots at Edwards Air Force Base surpassed 2,000 flight test hours in over 900 missions. One of the key advances in the Raptor's design is its advanced cockpit and integrated avionics system. Key mission systems include the Sanders General Electric Electronic Warfare System, the Martin Marietta Infrared and Ultraviolet Missile Launch Detector, the Westinghouse Texas Instruments Active Electronically Scanned Array Radar, the TRW Communication, Navigation, Identification Suite, and the Long Range Advanced IRST currently being tested. The electronic support measures systems radio frequency receivers give the aircraft the ability to perform intelligence, surveillance, and reconnaissance tasks. The F-22 features a glass cockpit with all digital flight instruments. The monochrome head-up display offers a wide field of view and serves as a primary flight instrument, while information is also displayed on 6 color liquid crystal display panels. The ejection seat in the F-22 is a version of the ACES II in U.S. Air Force aircraft, featuring a center-mounted ejection control. The F-22 is equipped with a sophisticated life support system, including an onboard oxygen generation system, protective pilot garments, and a breathing regulator anti-G valve that controls the flow and pressure to the pilot's mask and garments. The Raptor carries a formidable array of ordnance. It has 3 internal weapons bays, a large main bay located on the bottom of the fuselage, and 2 smaller bays situated on the sides of the fuselage, aft of the engine inlets. The main bay is divided along the center line and can accommodate 6 launchers for beyond visual range missiles, while each side bay contains a launcher for short-range missiles. The primary air-to-air missiles are the AIM-120, AMRAAM, and the AIM-9 Sidewinder, with plans to integrate the AIM-260 JATM in the future. Missile launchers require the bay doors to be open for less than a second. During this brief time, pneumatic and hydraulic arms push the missiles clear of the aircraft to minimize detection and allow deployment during high-speed flight. Although the F-22 typically carries its weapons internally, the wings feature 4 hardpoints, each rated to handle 5,000 pounds or 2,300 kilograms. Each hardpoint can be equipped with a pylon capable of carrying a detachable 600-gallon, or 2,270 liters, external fuel tank, or a launcher holding 2 air-to-air missiles. In addition to its armament of 8 missiles, the fighter is also equipped with a gun. At one point during the evolution of the Advanced Tactical Fighter program, the U.S. Air Force considered eliminating the gun to save weight. By the late 1990s, pilots involved in the Raptor program were confident that their aircraft could easily outperform and defeat any other fighter. This confidence, however, was based primarily on controlled flight and missile firing exercises. What these pilots truly needed was combat experience, and they were about to get it. The F-22 is equipped with an internally mounted M6 1A2 Vulcan 20mm rotary cannon, embedded in the right wing root with the muzzle covered by a retractable door. The cannon's firing path is displayed on the pilot's head-up display. Before the F-22 Raptor enters operational service with the U.S. Air Force in the autumn of 2005, it will undergo thousands of hours of rigorous combat testing. Despite this, critics of the F-22 program argue that the F-15 Eagle, which the Raptor is intended to replace, already possesses the attributes necessary to remain the world's premier air superiority fighter well into the new millennium. This view is dismissed by the U.S. Air Force. In March 2003, supporters of the F-15 were given the opportunity to test whether the Eagle was still the best fighter in the sky. 5 F-15s were pitted against a single Raptor in a head-to-head exercise. Although no missiles were used, the sorties closely resembled actual combat, with no quarter given by either side. It was a kill or be killed scenario. All 5 F-15s were piloted by experienced F-22 pilots. One by one, the Raptor brought them down. In these combat tests against F-15s, the F-22 Raptor decisively proved its critics wrong. In December 2005, the U.S. Air Force announced that the F-22 had achieved initial operational capability. During Exercise Northern Edge in Alaska in June 2006, 12 F-22s engaged in simulated combat exercises, downing 108 adversaries with no losses. Over the course of these exercises, the F-22 achieved 241 kills against 2 losses, neither of which involved an F-22. Due to U.S. federal law aimed at protecting its stealth technology and classified features, the F-22 cannot be exported. Instead, U.S. fighter customers are opting for earlier models like the F-15 Eagle and F-16 Fighting Falcon, or the newer F-35 Lightning II. The F-35 incorporates some technology from the F-22 but is designed to be more affordable, flexible, and exportable. Originally, the U.S. Air Force planned to acquire 750 ATFs. However, by 2009, the program was cut to 187 operational aircraft due to high costs, a lack of air-to-air missions because of the focus on counterinsurgency operations, a ban on exports, and the development of the more affordable and versatile F-35. The last F-22 was delivered in 2012. The F-22 Raptor was conceived amid Cold War fears that Russian-made fighters might outclass the F-15. Yet, as the world has evolved since the Cold War, the United States Air Force remains the sole operator of the F-22 as of August 2022. It has 183 aircraft in its inventory. In today's changing world, there are few certainties, but the F-22's dominance over the skies remains one of them. The F-35 was the product of the Joint Strike Fighter, or JSF, program, which was the merger of various combat aircraft programs from the 1980s and 1990s. The Lockheed F-35 Lightning II, unofficially nicknamed the Panther, is a fifth-generation strike fighter development of the United States that incorporates new and learned stealth technology and practices with advanced computer processing and systems through a modular approach. The primary objective of the project was to create a versatile aircraft capable of meeting the needs of multiple branches within the U.S. Department of Defense, including the United States Air Force, the United States Navy, and the United States Marine Corps. To achieve this goal, the F-35 program developed 3 interconnected but distinct airframes, all based on a single-engine, single-seat design. Although there are variations between the production models, all versions of the aircraft retain the supersonic capabilities and possess unparalleled strike capabilities, making them unmatched by any other modern battlefield platform. The F-35 program evolved to become an international effort beyond the commitments of the United States and the United Kingdom, and have included Australia, Canada, Denmark, Italy, Netherlands, Norway, and Turkey to varying degrees. Each nation is expecting to operate the F-35 platform in number at some point, and each player is rated by partner levels in the development. The Joint Strike Fighter program was started on November 16, 1996, as a U.S. attempt to develop a next-generation combat airframe capable of replacing a variety of dedicated fighter and fighter-bomber types then in the U.S. war-making inventory. The new design would have to succeed such proven performers as the Lockheed F-16 Fighting Falcon, the Fairchild Republic A-10 Warhog, the carrier-based Boeing FA-18 Hornet, and the McDonnell Douglas AV-AB Harrier II. No small task, considering the respective successes found by each aircraft throughout the world for time in aviation history. The F-35 originated from the U.S. Joint Striker Fighter, or JSF, program, and went through a 5-year competition phase known as the X-35 against Boeing's X-32. Although both aircraft met the requirements, Lockheed's submission was chosen over Boeing's because it consistently outperformed the latter and was considered a lesser financial risk in the long term. Boeing's X-32 utilized a more conventional vectored thrust approach, similar to the Harrier, for vertical and takeoff maneuvers. In contrast, a third proposal from a Northrop Grumman McDonnell Douglas team presented an interesting lift plus lift cruise methodology akin to the Soviet Yakovlev Yak-38 Forger. Lockheed's approach involved a dedicated lift fan system positioned at the aircraft's center mass, just aft of the cockpit, combined with a rotating rear engine exhaust nozzle to achieve a balanced result. Both propulsion units derived lift power from the single engine, and Lockheed's patented lift fan was considered a more feasible long-term solution. The lift fan concept had distinct advantages over the X-32's thrust vectoring system, as it offered cooling for the downward thrust air, reducing the risk of hot exhaust gases re-entering the engine. Additionally, the space saved by the lift fan drive system allowed for increased internal fuel storage in the proposed X-35A and X-35C conventional fighter versions, thus enhancing their operational ranges. This feature was particularly appealing to the USMC, which prioritized a short-range, quick-react aircraft for their STOVL version, the X-35B. Winning the X-35 contract was a significant achievement for Lockheed, with potential revenues of up to $200 billion through the X-35 program and subsequent F-35 production phases. Pratt & Whitney, the engine manufacturer, secured a $4 billion contract for their primary engine supply and development. Additionally, the British government invested $2 billion into the project with the hope of acquiring their first fifth-generation and first stealth fighter aircraft. The production version of the F-35 aircraft originated from 3 X prototypes, with the first one being the X-35A, manufactured at the Skunk Works facility in Palmdale. The X-35A successfully completed its maiden flight on October 24, 2000, and then underwent extensive trials, including in-flight refueling and supersonic flights at Edwards Air Force Base. After concluding 27 flight tests on November 22, 2000, it was converted into the X-35B STOVL variant prototype. Meanwhile, the X-35C, serving as a backup to the more complex X-35B development, was prepared to accept the lift fan assembly if needed. The first production F-35 Lightning II took its inaugural flight on December 15, 2006, and the first F-35A completed its flight testing at Edwards Air Force Base on October 23, 2008. Soon after, on November 13, 2008, supersonic flight was achieved. The X-35B achieved its first flight on June 24, 2001, demonstrating a complete and sustained hover cycle, conducting 8 vertical takeoff operations and 27 hover landings. The production STOVL F-35B began its flight testing phase in 2008, with the first F-35B taking its first flight on June 11, 2008, and the second F-35B completing its maiden flight on February 25, 2009. The first aerial refueling exercise for the F-35B was successfully accomplished on August 13, 2009. The carrier-capable X-35C made its maiden flight on December 16, 2000, and subsequently underwent a series of rigorous mock carrier landings to assess the modified airframe performance. The X-35C demonstrated excellent low-level, low-speed approaches that the U.S. Navy sought in their new combat aircraft. After completing a total of 73 test flights on March 11, 2001, the production 35C was revealed on July 28, 2009, with its expected first flight scheduled before the end of 2009. The F-35 test program reached a milestone with its 100th flight on June 23, 2009. Initially, the F-35B for the USMC was anticipated to be delivered around 2012, making it the earliest of the 3 variants, while the U.S. Air Force expected deliveries of its F-35A model in 2013. The U.S. Navy's F-35Cs were expected to be delivered in 2015. The projected lifespan of the F-35 airframe extended beyond 2030 and was estimated to continue into the 2040s. The F-35 is equipped with an advanced electro-optical distributed aperture system, or DAS, that provides the pilot with a comprehensive view of the battlefield from all angles of the aircraft. The DAS enables the F-35 to detect and coordinate enemy aircraft, air-to-air and surface-to-air missile launches, and ground explosions. Both the short takeoff and vertical landing, or STOVL, and conventional landing variants feature high levels of automation to streamline operations. The aircraft also offers enhanced pilot vision for day and night sorties. The DAS system was developed by Lockheed Martin Missiles and Fire Control in collaboration with Northrop Grumman Electronic Systems. Additionally, the F-35 is equipped with an all-new electro-optical targeting system, or EOTS, developed by Lockheed Martin and Northrop Grumman. This targeting system provides the pilot with enhanced target detection and tracking capabilities at extended ranges, making the F-35 one of the most lethal combat aircraft in the skies. The EOTS is located on the underside of the nose assembly. Stealth technology advancements learned from the Lockheed F-117 Nighthawk stealth fighter have been extensively incorporated into the F-35 Lightning II design. The engine nozzle is designed to be stealth-friendly and axis-symmetric, reducing the aircraft's radar signature while maintaining a minimal profile. The F-35 avionics suite, produced by Northrop Grumman Space Technology, features data-sharing capabilities, allowing the pilot to share real-time information with allied air and ground forces through a satellite data link system. The communications suite, developed in collaboration with international partners, ensures robust and adaptable communication capabilities. For situational awareness, the F-35 is equipped with an AN/APG-81 series active electronically scanned array, or AESA, radar developed by Northrop Grumman Electronic Systems. This radar system enables the pilot to detect, track, and engage targets on land, water, or in the air over significant distances. The radar can also operate as a passive receiver. To enhance pilot situational awareness further, the Distributed Infrared System, or DIRS, consists of 6 internal sensors strategically placed around the aircraft. These sensors provide a real-time infrared image of the aircraft's surroundings, projected directly into the advanced helmet worn by the pilot, offering a complete 360-degree view. The F-35's engine inlets are designed with diverterless fixtures, reducing weight and complexity by minimizing moving parts. The aircraft features a helmet-mounted display system, or HMDS, developed by Vision Systems International, LLC, which delivers critical mission and system data directly to the pilot's helmet visor. This advanced system eliminates the need for a conventional heads-up display and allows the pilot to track and engage targets without facing them directly. The cockpit is equipped with a large panoramic multifunction display system, providing real-time information and high-resolution imagery. The F-35's cockpit supports direct voice input through a speech recognition system and incorporates a Martin Baker US-16E ejection seat. Flight control is achieved through a conventional hands-on throttle and stick setup. The F-35's onboard systems are highly configurable, allowing adaptability to various mission requirements, whether it's air superiority or ground strike operations. With its cutting-edge technology and unparalleled capabilities, the F-35 Lightning II is a force to be reckoned with in modern aerial warfare. The primary propulsion for the F-35 is provided by a single Pratt & Whitney F135 afterburning turbofan engine. Initially, a second engine option, the upgraded F136, was in development under a joint effort by General Electric and Rolls-Royce. However, development of the F136 was terminated in December 2011. The F135 engine is an afterburning turbofan, delivering 28,000 pounds of thrust on dry power and up to 43,000 pounds with full afterburner engaged. Positioned in the middle rear portion of the fuselage, the engine allows the F-35 to reach a maximum speed of Mach 1.61 and soar to altitudes exceeding 50,000 feet. The rate of climb and G limits vary based on the variant, with the A model having a 9G limit rating. For the F-35B production model, vertical flight capability is achieved using the Lockheed Martin patented shaft-driven lift fan. This lift fan system, built by Rolls-Royce Corporation of Indiana, consists of the fan itself, a clutch, 2 roll posts, and the drive shaft connecting the lift fan to the power plant. Working together with the 3-bearing swivel module, the thrust vectoring nozzle at the aircraft's tail, the lift fan enables balanced lift during vertical flight. Powered by a 2-stage turbine on the engine, the lift fan can generate up to 20,000 pounds of lift, nearly half of the total vertical flight thrust. Additionally, the lift fan provides cooling for the downdrafting air, which is an improvement over previous short takeoff and vertical landing systems. The airflow through the fan is regulated by variable inlet guide vanes. Standard armament for the F-35A production model is the GAU-22A 4-barrel 25mm cannon with 180 rounds afforded. The F-35B and the F-35C also feature this weapon, though through an external mounting and given 220 rounds. The pod itself sports stealth designing to keep the signature of the F-35 airframe in check. To comply with its stealth requirements, the F-35 typically houses its primary ordnance in internal bomb bays, while 6 optional external underwing pylons provide the bulk of the weapon's payload carrying capability. Because of the F-35's international appeal, the aircraft is capable of fielding some foreign-born weapon systems available in the UK, Israel, and the NATO arsenal. Some analysts have criticized the F-35, claiming it to be overly complex, deficient, and prone to breakdowns. Additionally, they argue that it may not be well suited for the missions it was originally designed for. Over 20 years of R&D, that lightweight replacement fighter got heavier and more expensive as the Air Force and lead contractor, Lockheed Martin, packed it with more and more new technology. Yes, we're talking about the F-35. The 25-ton stealth warplane has become the very problem it was supposed to solve. And now America needs a new fighter to solve the F-35 problem, officials said. With a sticker price of around $100 million per plane, including the engine, the F-35 is expensive. While stealthy and brimming with high-tech sensors, it's also maintenance-intensive, buggy, and unreliable. The F-35 is not a low-cost, lightweight fighter, said Dan Ward, a former Air Force program manager and the author of popular business books including The Simplicity Cycle. Brown's comments are a tacit admission that the F-35 has failed. As conceived in the 1990s, the program was supposed to produce thousands of fighters to displace almost all of the existing tactical warplanes in the inventories of the Air Force, Navy, and Marine Corps. The Air Force alone wanted nearly 1,800 F-35s to replace aging F-16s and A-10s and constitute the low end of a low-high fighter mix, with 180 twin-engine F-22s making up the high end. But the Air Force and Lockheed baked failure into the F-35's very concept. They tried to make the F-35s do too much, said Dan Grazier, an analyst with the Project on Government Oversight in Washington, D.C. The complexity added cost. Rising costs imposed delays. Delays gave developers more time to add yet more complexity to the design. Those additions added more cost. Those costs resulted in more delays, and so on and so forth. 15 years after the F-35's first flight, the Air Force has just 250 of the jets. The F-35 has not had a trouble-free path in its fielding, nor has any new combat aircraft. The reality is that each generation of combat aircraft push technology to the edge, and this involves distinct challenges and a learning curve. The real question is whether the trends of mission capability, availability, unit, and operational costs are headed in the right direction. In the case of the F-35, this is certainly the case. For the members of Congress slated to attend this week's oversight hearing, it may be worth recalling the advice of Sir Frederick Handley Page, a British aviation pioneer. Nobody has ever won a war by trying to run it on the cheap. Nothing is so expensive as losing a war by saving money. If you want the cheapest possible Air Force today, it is very easy to standardize on a whole lot of aircraft that will be of no use when the war comes. For 80 years, Skunk Works has pushed the innovation envelope, failing fast to prove out novel technologies and deliver disruptive solutions for our customers. Strap in as we take a quick trip through the years to reflect on the critical work Skunk Works has accomplished, all of which informs the work we're doing today and in the future. As we look at the technologies Skunk Works continues to develop now and for the future, it's just as exciting and as classified as Skunk Works' illustrious history. Work continues in critical areas like UAS, hypersonics, artificial intelligence, low observables, and other revolutionary technologies. A prime example that is not being developed under the cloak of secrecy is the team partnering with NASA to develop and build X-59, the prototype that will quiet the supersonic boom. The way we engineer and build these capabilities is evolving too, as we lean more and more into a digital approach that reduces cost and accelerates development. The unique and proven Skunk Works philosophy has enabled the impossible to become reality for 80 years. This dedicated and growing team continues to embrace Kelly Johnson's motto, "Be quick, be quiet, and be on time." We innovate with urgency to push the boundaries, ensuring our customers have the capabilities needed to stay ahead of ready.
My name is Harold Carlson Farley, Jr., and I was raised under the name of Carlson. When my wife gets serious, she calls me Carlson, but everybody else calls me Hal. And I got that from the military as being Harold to Hal. Skunk Works. Back in 1943, I believe it was, the United States Air Force realized that the Germans were fielding a new jet airplane called the Me-262, a twin-engine jet that was capable of reaching our long-range bombers, the B-17s. So they felt that they needed a jet airplane. We needed a jet airplane for the Air Force. And so they contacted Lockheed for the job. I'm not sure exactly what their motivation was to come to Lockheed, but Kelly Johnson was a pretty well-known airplane designer and had been instrumental in the P-38, which was a first frontline fighter in the war. Anyway, they came and they said, "We need an airplane in 5 months, a jet airplane in 5 months." And Kelly Johnson, who was a well-thought-of young engineer who had a very strong personality and a great amount of leadership capability and very strong man. He said, "I'll take on the job. It has to be done by my rules." He had 14 basic sets of rules. I can't name all 14 of them, but 2 or 3 of them are important. One, he gets to select the very best people he has in the whole company. Number 2, he reports directly to the company president. 3, nobody else interferes with the project at all. It's his project, and he's the boss, and the rest of the people in the Skunk Works are workers. So anyway, those are the rules that he set up for taking on that project. And it took the Air Force a month to deliver the proposal, but in the meantime, he'd already started working on the airplane, knowing full well he was going to be doing it. And they managed to deliver the airplane in 143 days. That comes out a bit shorter than 5 months, 4 months and some days, which was pretty phenomenal when you think about it. And it was a pretty advanced airplane. It was the XP-80 and made its first flight in 1943. And the pilot at controls was a fellow by the name of Milo Burcham, who was later killed in an accident. That was how the Skunk Works got its start and its reputation of being able to do a job quickly, on time, and under cost. Well, the name Skunk Works was from the Little Abner comic strip, where I can't remember the character, but he was up in the woods and he would brew up this kickaboo joy juice, some white lightning, I guess, and it smelled bad. And there were some odors that were in the hangar area of Burbank there. And so one day, one of the engineers answered the phone and said the Skunk Works, which was spelled S-K-O-N-K. And everybody started calling it Skunk Works, but the creator of Little Abner said, no, you can't use that. And went to court over it. I guess we probably conceded. I don't remember if there's any details of that, but we changed from Skunk Works to Skunk Works, and that's stuck, and we've always had the emblem of a skunk on the tail of the airplanes. The year I joined the Skunk Works was 1978, and I joined because I had been working with a fellow, Dr. Ken Stewart. He had a PhD in plasma physics, and he and I had been working on a new head-up display for the F-14. I was working for Grumman at that time, and unbeknownst to me, was also assigned to the head-up display for the new stealth fighter that was being developed at the Skunk Works. I read in the newspaper, in the Los Angeles Times, a very short paragraph that said a pilot had been injured in the desert. His name was William Park, and there was no details in that little thing, that little clip. And I always remember reading that and realizing or thinking that's very unusual. There's something going on up in the desert that they're not telling anything about, but they had to say something about the accident. It was my future boss who was in that accident, and he needed a pilot because he had injured himself pretty bad. He had asked some people around, and Ken Stewart recommended me. He called me one day. He was very abrupt on the telephone. He said, "My name's Bill Park." He said, "Would you be interested in a job at Lockheed?" And I said, "Well, you'd have to tell me something about it." Well, he said, "It's at the Skunk Works." You know, the Skunk Works is a magic word among pilots, and I was immediately interested when he said that. I said, "Yeah, I would be interested if you could tell me something about it." He said, "Well, I'll call you back." And that was the end of that conversation. For about 3 weeks, I figured it went away and wasn't coming back. But he did call me back, and he said, "Have you thought about it?" I said, "Yeah." I said, "I would be interested." And he said, "All right." He said, "I'd like for you to come down for an interview." He said, "But I don't want you to come to the company. I want you to come to my house." And so I said, "Okay." He gave me the address, and it was down in Westwood. And the house was on the golf course in Westwood, down in the high rent district of L.A. And it was a gorgeous home. And I mean, it was a beautiful home, and there was nobody there. His wife wasn't there. She was somewhere else. And he greeted me, and I came in, and we had our chat. And when I left, I said, "Man, those guys must pay a lot of money." Turns out that Bill and his wife were really good at real estate. But that was how I got introduced to the Skunk Works. It took about 3 months to get a clearance. I had a secret clearance from Grumman, but this was secret special access required, which is a couple of levels above secret to be able to access the program. So I was placed in the penalty box, they called it, until the clearance came through. And then when it came through, they then could introduce me to what it was we were going to fly. And I remember Alan Brown was one of the senior engineers, and he took me into a room, and the drawings were up on the wall, regular blueprint drawings, and he said, "What do you think of that?" And as you know, it's a very unusual looking airplane, and it's very highly swept angles. And my first thought was the darn thing must be a reentry vehicle. It had to be something like that. And then he explained it to me what it was for, that it was to evade radar. And I really didn't pick up on how important that was at the time. I thought that was okay, good. It's evade radar. How well does it fly? Is it a real fighter? Can we shoot things down with it? You know, what a pilot wants to do is be able to maneuver his airplane well. And it turns out the airplane is pretty, low performance, relatively speaking, to the current day fighters. And so that's how I was introduced to the airplane. And then I was assigned to the weapons system to work on the displays with my old friend Ken from Grumman, who was working down there at Lockheed and at Grumman at the same time. Well, the first prototype was on the floor. What was available was the wooden mock-up. They had a complete wooden mock-up, full-scale wooden mock-up they were using to do the wire runs in. This is really crude, manufacturing process quite a few years ago, but they were using this wooden mock-up to place displays in the cockpit, to locate boxes and, see if they would fit. And we also had offices right alongside that, and we had people that were working on the displays, and I was assigned to the cockpit displays, and we had two other pilots that were working on other aspects of the airplane as well with the engineers. I think it was for two reasons. One, I had been a test pilot in industry for a number of years. The other fellows had come directly from the military. It isn't that you can fly any better. It's just that how do you deal with engineering and the company? And I was, I think, better prepared to do that than the Air Force guys that were, and another Navy guy that came in. I think that was one of the reasons. And the other reason is I worked like the devil. I worked hard because I wanted to be the project pilot on it. And I was selected. That's what I think was the reason. In order to be able to be the project pilot and the first flight pilot, the competition for that is intense. You want to be the guy that gets the job, and you work hard. You work with engineering. You work with and you're flying. We are flying at the time. We were flying airplanes like T-38s, and so you're being evaluated by the boss and also the customer. It is something that I don't know how to describe it any other way. It's an intense process. The secrecy, the classification of the program was at the same level as the Manhattan Project. That was how secret it was, and it was very successful. If you recall, we spent many years working and actually having the airplane in operational readiness, and not many people knew anything about it. And so it was highly classified, remotely developed, a lot of time away from family. We spent usually 6-day weeks, and we would leave home and come back after Friday or Saturday night, and then turn around and go back out Monday morning. For, well, I guess probably the first year and a half was that we were separated that much. My wife knew I was flying. I mean, that was my job, but that was all I could tell her. I couldn't tell her what I was flying, where we were. We had a special arrangement, secure telephones, so we could call home through the office fairly regularly, and not have to worry, just to check in and see how everything's going as the hot water heater broken down or whatever. But yeah, it was pretty strenuous on the family life. People that I associated with knew know about the Skunk Works. They know you're going to say, "I can't tell you." There's nothing I can tell you about it. I can say this: the Air Force were flying A-7s as a cover airplane. They had a squadron of them at Nellis Air Force Base, which were supposedly working on some advanced system, and they were kind of secret. But that's where the Air Force was. They used the A-7 as their cover story. Our cover story was just simply we just didn't talk about it. The security that was established within the Skunk Works, the security or the classification culture of the Skunk Works was developed by Kelly Johnson again. And back to the a little bit about that initial airplane that he built, the XB-80 that started the Skunk Works. One of the requirements was it had to be top secret. And one of the reasons for that is it keeps other people out. That was one of the tools to keep other people from becoming involved with the program, from becoming a bureaucracy. So the Skunk Works security was established out of common sense. For example, if you put a guard out in front of a place, somebody's going to know something's inside. They didn't put any guards out. If you put secret or confidential on a drawing of an airplane, you're going to know it's a secret. Something's going on if somebody gets a hold of it. They didn't stamp any of the things classified at all. They didn't have any guards outside. They made it as normal as possible so as to not attract attention. They went so far way back when the satellites were first coming out, and they took all the names off of the parking places because they could find out who was working there. The enemy could find out who was working there, the enemy being the Cold War and Russia. The Skunk Works operated out of Burbank and has operated out of Burbank all the way back to the P-38, to the U-2, to the SR-71, to F-117. All of them have been built there and down in beautiful downtown Burbank, inside a big old World War II hangar. The airplanes were assembled there. Then the wings were taken off of them, and in the case of the F-117, they flew a C-5, which is the Air Force's huge cargo airplane. They'd fly it in the middle of the night, and they would take the phone calls for the noise abatement because there's always somebody in the neighborhood who didn't like the noise, but it only happened every now and then, so we kind of disregarded it. But anyway, they would make a box frame out of wood, 2x4s, and drape a tarp over it so it would not show any part of the shape of the airplane whatsoever. And they put it on wheels, and they would wheel it out, put it in the C-5, and then they would fly it off to where we would test the airplane. And it was reassembled and then tested at a remote location. And that was done, in fact, back in the SR-71 days, they didn't have a C-5A to transport that around, so they developed a false front, if you will, for a truck line. Lockheed had a trucking company that was named some weird name, and it was on the back of those trucks that they hauled the SR-71 fuselage and wings to the test location. The first flight was a success, I'll say that, because we took off and we landed. But there were some problems that we encountered and some things we discovered that needed to be fixed. But let me go back just a little bit. The airplane is unstable in pitch and yaw. It can't be flown without the assistance of computers. At the lower speeds, it's about neutrally stable, which is almost flyable. One of the bits of information that goes to the computers to help fly that airplane is the air data that goes in the probes on the front of the airplane. And the engineers were afraid that the vibration of those probes on takeoff and in turbulent air might send vibrations to the flight controls and cause them to oscillate. And so therefore they did not want to use the air data on the initial takeoff. So what we did was we put a bunch of lead in the front of the airplane and made it positively stable, thinking that I could manage the airplane. It was still not real stable, but it was stable enough that we felt that I could fly the airplane satisfactorily up to 10,000 feet and then turn on the air data information to the computers so that if it did cause a problem, there would be plenty of room between me and the ground to get those things turned off again and bring the airplane back. That was the plan, and that's what we did. We took off, ballasted with lead in the nose so that it was slightly stable on takeoff, which was fine. The rotation and everything was good in pitch. It was that the fact that the airplane started to yaw, and it went out, I believe it was 6 degrees to the left, and then I tried the rudder to stop it, and it didn't respond right away, and then it slowly came back the other way and went out to around 12 or 13 degrees the other way, and that's very uncomfortable in an airplane to feel like you're skidding sideways. And so I realized that this thing wasn't acting the way we expected to act based on the wind tunnel and simulation that we'd done. Actually, I had 3 switches for pitch, roll, and yaw over on the left-hand console, and the yaw switch I had extended because that was the most critical one. And I turned on the air data so that it would come to through the probes and go to the flight control computer to help me fly the airplane. And it did. It worked fine. There were no vibrations or anything like that. But they got turned on a lot quicker than we planned to do because we were going to go to 10,000 feet to turn them on. Based on that information, we realized that the fins on the airplane, the tail fins on the airplane were considerably too small. The wind tunnel data, I don't know how a mistake was made. Somehow, I believe I heard that they didn't take into full account the sting that the pole that you put an airplane in a wind tunnel on contributes to stability. And I'm not sure that's the case. At any rate, they came up with a figure that they said we were going to be more stable than we really were. So the fins were too small, and that was the big discovery on the first flight. And we flew the airplane 6 more times in a very limited flight envelope while they were building a new set of fins 50% bigger that were put on the airplane. And from that point on, we had the proper amount of stability. That was the big thing learned on the airplane. The minor problems that we occurred are not minor, really. We had overheat in the tailpipes because the tailpipes were rectangular, and in the corners, heat builds up. And they were reaching limited temperatures. And we also had the canopy unlock light that came on, and that was of concern because if the canopy had come off, you get a face full of wind, and it was marginal about whether you could land the airplane or not. And the other thing was that we heard a big thump, and that was the blow-in doors, which were spring-loaded and activated so that it gave enough air for the airplane on the ground, enough air to the engines to run properly, and then as you accelerated, more air came in the inlets, and then the doors would spring-load shut, making the airplane stealthy because you can't have openings in the airplane and be stealthy. And when they slammed shut, there was 2 very pronounced thumps that I hadn't anticipated, scared the heck out of me. But there was no indication in the control station nor on my instruments, so we continued on with the flight. The flight was only 15 minutes, limited by the temperature in the tailpipe. And that was basically the first flight, yeah. No, I've never had a UFO sighting.
Okay, that's good.
How we worked together at the Skunk Works and with our customer was absolutely critical to the success of that airplane. The airplane was a huge success. The program was a huge success. In the world of flight test, in the last 30, 40, 50 years, there's always been a aura of competition between the company pilots and the customer pilots, the Air Force pilot or the Navy pilot that's going to be getting the airplane. Ever since I started the testing business, I was a Navy test pilot for a long time, and then I became a civilian test pilot for Grumman, flying F-14s and A-6s, and it was always a us and them battle, you know. We felt like we could do it better as company pilots than they could. It was just kind of, I know, testosterone, ego, whatever you want to call it. It was always a scrap. And I learned from this experience that cooperation works a whole lot better than adversarial relationships. Kelly Johnson's, one of his basic rules was, we need to be allowed to test our product, otherwise we will never be able to, advance our products in the future. So he felt like he needed a corporate knowledge in the form of pilot experience in the airplanes that he built. And the Air Force has always felt that they wanted to do all the flying. It's always been a compromise. If you have a combined task force, typically the company does fly the first flight of the airplane and does flutter and does structural and does all that stuff, but the operational aspects are done by the customer, which I think is a good way to do it. But there's always a little bit of a conflict. But we had a very unique individual in the Air Force, a guy by the name of Skip Anderson, who was running the Air Force side of the test force. He had a very unique way of calming us company pilots down. He provided great leadership, and he worked well with Ben Rich, the head of the Skunk Works, and they got along great, and we saw that, and we all followed suit. And I give Skip a lot of credit for that. We got along very well. John Beasley was one of the Air Force guys, and he was just one of the team. We were all teammates. One of the criteria for working at our remote location is you had to get along. If anybody didn't get along, you were out of there. So teamwork and cooperation were fundamental to the success of the program. What does it take to make a good test pilot? I think one of the things is the basic flying skills need to be above average. I think that responsibility to the company and to the product are fundamental to being a good test pilot. I think involvement with the design and development of the airplane is critical to being a good test pilot. I think an engineering degree or advanced degree is, in this day and age, the kids that go off to the test pilot schools, they arrive there with master's degrees, and a lot of them go away with PhDs. You know, they're way above me. I only had a bachelor's degree, but it's hard for me to say. I'm telling you about what I think I am. You know, am I an above average pilot? Yeah, I am. I can say that honestly. Am I one of those great stick and rudder guys like Bob Hoover, who was a phenomenal pilot, is a phenomenal pilot? I'm not one of those. But do I get involved with the project? I do. I get very involved with the project, or did when I was working. Well, first of all, if I were talking to my grandson, who they're all grown up, my great-grandsons, I would say first thing is honesty. Be totally honest. If you can't be honest, then you're going to tell somebody something that you did that you didn't do. And I learned that really early in test piloting game. Several people had made a mistake. It was a simple mistake. They left a switch in the wrong place. And if you took off an afterburner, you were dumping fuel and it would light up and you'd leave this big long torch behind the airplane. And I did that. And I came back and I convinced myself that that switch was in the right place and that I didn't switch it, but I did. And so I was embarrassed by that. I got caught with my hand in a cookie jar, and that was my real lesson in honesty. You have to be honest as a test pilot. You can't, if you made a mistake, man, you got to tell them, because otherwise they might blame it on the airplane, or they might, the manufacturing process may be changed, or the engineering process. I learned, as I mentioned in the last bit of discussion, that to work with people, you have to respect them, you have to respect their ideas, and you have to present yourself as their co-equal. Honesty, integrity, care for other people. In the world of test piloting, once a guy gets to be the chief test pilot, it is normal for the chief test pilot to go out and fly all the good stuff. And that was the way it was at Grumman. There was a man by the name of Corky Meyer for years was the chief test pilot, and anytime a goodie came up, a first flight or a bonus flight, we got extra pay if it was hazardous. The lead guy, the chief pilot, would end up going out and doing it. There was a fellow there that worked at Grumman, and I won't mention his name, became the chief pilot, and he did everything. And the rest of us were doing the dog work. And I said, if I ever get to be chief pilot, I'm going to share the load a little bit. And those guys, I got to be the first flight pilot. There's two other guys that were very lucky that I got to be the first flight pilot in the F-117. Because I said, if I got to be chief pilot, as I said, I would share. And I had two guys working for me we were very close, Dave Ferguson and Tom Morgenfeld. Dave was an Air Force guy. Tom was a Navy guy. When it came time for the F-22 to come along, I had plans. I was dreaming about sailing around the world, and I was getting to be, closer to 55. And so I said, I'm going to do what I said I was going to do, and I gave Dave Ferguson the project pilot job. I was the chief pilot and director of flight ops, but he was the project pilot and would be flying the first flight on the F-22. The day he went out and flew that first flight, I was out there watching it, and I was saying, man, I wish I had made hadn't made that promise, but I was very envious of the day he got to fly. I would have been able to fly the airplane if I'd have just exercised my rights as the chief pilot. And then the next airplane, the F-35 that came along, Tom Morgenfeld got to fly the first flight. So each one of us got a first flight, and I'm kind of proud of that. We had T-38 Talons, we had A-7s, we had F-4s, all of which we could fly anytime we wanted to. And that was that was like the astronauts had. You know, they had their airplanes were out there. Anytime you wanted to go fly, you can go fly. And it was good. It maintained proficiency. It wasn't just a good deal. And we did a lot of air-to-air stuff. And we'd go out and fight each other. That was very good for confidence and very good for proficiency. The F-14 flies like a small airplane. It's a big airplane, but it flies well. Flies small. I enjoyed the A4. The A4 is a little sports car. You know, it's got 270 degree per second roll rate. Put the stick over and you're through 360 degree rolls about that quick. And of course the F-117, which turns out to be, we tailored the flight control system so well that it's very easy to fly. I mean, it feels just like a normal airplane and one of the best of the normal airplanes. Like an F-15 is very easy to fly. Very easy to land, very easy to take off, and excellent flying qualities. The reason that the F-117 was retired was because of the F-22. The F-22 is a high-performance airplane. It can do what the F-117 can do. It carries its weapons internally. It can deliver air-to-ground. It can deliver air-to-air. It can go supersonic. It can cruise supersonic. And it's aerodynamically shaped. And you notice it has curved surfaces, and the F-117 has flat surfaces. And the reason was when we designed and built the F-117, the original program was not nearly as sophisticated as the programs they are using now to predict and develop stealth shapes. And so we had to go with flat surfaces, flat and angles. So that's where they differ. That's just and the money required. And then there's rumor around. It was mentioned the other day by a friend of mine talking about Aviation Week had an article that they've seen an F-117 flying. And that would really make me feel good.
We knew that, overflying Russia for 4 years, that they were making important advances in radar and missiles. And so in 1958, 2 years before Gary Powers was shot down, we decided we'd try to make a follow-on airplane, which became finally the SR-71, to fly higher and 4 times as fast. So that's the connection between the grandfather type and the SR-71.
Everyone called him Kelly. And as he reminisced that day about the genesis of his Mach 3 masterpiece, he could have just as easily reflected back on a time when aircraft designers were striving for 200 miles per hour, a time when he landed his first job with the fledgling Lockheed Aircraft Company. In 1932, a small group led by Robert E. Gross had purchased Lockheed out of bankruptcy for $40,000 and staked the company's future on the development of an all-metal, twin-engine transport. Models of the design were sent to the University of Michigan, where a young graduate student named Clarence L. Johnson conducted wind tunnel tests. Although his faculty advisors gave the design a passing grade, he wasn't much impressed, and after he had been hired on as a tool designer at Lockheed in August of 1933, he let Chief Design Engineer Hal Hibbard know about it. Among other things, it'd be directionally unstable, especially with one engine out. A rather presumptuous and certainly unconventional way for a 23-year-old to start his career with a new company, but it was only a hint of what would follow. The son of Swedish immigrants, he'd been nicknamed Kelly by classmates because of his quick temper, stubborn tenacity, and unwillingness to back down from a fight, even against overwhelming odds. Instead of reminding the outspoken young man of his place, Hibbard suggested he go back to the wind tunnel and see if he could improve the design. After 72 test runs, he came up with the solution, an unconventional twin-tail arrangement soon to become a Lockheed trademark. And the Model 10 Electra became the foundation for Lockheed's future growth, as various models of the airplane helped revolutionize commercial air transport in the 1930s. With his work on the design, Kelly Johnson became the sixth member of an engineering department in an industry which then couldn't afford specialists. Working, often simultaneously, as an aerodynamicist, stress analyst, weight, wind tunnel, and flight test engineer, he also put in long hours out in the shop, getting hands-on production experience and learning firsthand the importance of designing producibility into an airplane. It was a real-world education on all phases of design and development that within a decade couldn't be duplicated, and the lessons learned became guideposts for the rest of his career. He flew, for example, as flight test engineer on all models of the Electra, and worked for some of the most notable figures in aviation, such as Amelia Earhart. Out of this experience came his lifelong conviction that the designer had to be able to test his own airplane. As he later commented,
I decided at an early age that unless I had hell scared out of me once a year, I wouldn't have the proper balance to really design new airplanes of any type.
Kelly Johnson would log more than 2,300 hours as a flight test engineer. The versatile Electra spawned two major developments. One was the XC-35, a modified Model 10, which in 1937 first demonstrated the practical feasibility of transforming the entire fuselage into a pressurized cabin to permit comfortable high-altitude flight. Johnson was Lockheed's flight test engineer on this project, gaining first-hand experience with the problems of pressurization, and more important, with the tremendous possibilities pioneered by this aircraft. Possibilities to which he and Hall Hibbard began to give serious consideration. Meanwhile, the Model 14 Electra incorporated a number of Johnson innovations, such as the first practical application of Fowler flaps, which both increased the wing's lifting surface and served to permit slower, shorter distance landings, an achievement which won him the 1937 Lawrence Sperry Award. In 1938, the high speed and innovative features of the Model 14 attracted British interest in its potential as an anti-submarine patrol plane. But the requirements necessitated a major redesign. Johnson worked around the clock for 3 days to transform the Model 14 into the Hudson bomber. The British ordered an initial batch of 250 aircraft, at that time the largest production order ever received by an American company. But there would be many more. 2,000 to the RAF alone, out of a total production run of nearly 3,000 airplanes. The Hudson put Lockheed into the big time. But even as production was gearing up, Kelly Johnson and his colleagues were well into other much more ambitious designs. The success of the pressurized XC-35 and the recognition that the next generation of air transports would be much larger, higher-speed, transoceanic aircraft inspired Johnson, Hibbard, and a small design team to lay out the now classic lines of the Model 49 Constellation in 1939. Using his soon-to-be legendary powers of persuasion, he convinced Lockheed to build its own wind tunnel, a decision that paid for itself many times over during the development of this design, as all aerodynamic problems were overcome early on, and not one external change had to be made to the actual aircraft. Hibbard was so impressed by Johnson's wizardry that he swore he could see air. Commercial development of the legendary Connie would be delayed by the war, and it first flew as the Army Air Force's C-69. This, however, provided time to refine the airplane so that at war's end, Lockheed was postured to capture a lion's share of the commercial market, and various models of the elegant Connie would continue to grace the world's airways into the late 1950s. At the time he laid down the basic design of the Constellation, Johnson was already well into another path-breaking project. In early 1937, responding to an Air Corps requirement for a high-altitude interceptor capable of 360 miles per hour, Johnson and Hibbard hastily conceived some possible configurations, depicted here in one of Kelly's rough sketches. As Johnson observed many times, In design, you're forced to develop unusual solutions to unusual problems. Their decision to go with an unconventional twin-boom configuration was dictated by another axiom. Design features are the creatures of necessity. The twin booms evolved as a logical development of engine nacelles which had to be extended to house the liquid-cooled engines, turbo superchargers, radiators, and main landing gear. It seemed logical, then, to simply extend the nacelles into booms which could carry the empennage. Their novel approach produced a winning design, and when the XP-38 was finally rolled out in January of 1939, its sleek lines bespoke speed. And when Lieutenant Ben Kelsey took it up for its maiden flight, it delivered an impressive 403 miles per hour, far exceeding the requirements. Thus began the saga of the P-38 Lightning. The first American aircraft able to fly at such speeds, it offered dazzling performance and a host of new problems. For as it peeled over into dives at high altitudes, it could hit speeds approaching 500 miles per hour. In this region, the aircraft began to violently shake and nose over into increasingly steeper angles, and control forces became so heavy pilots couldn't pull out. Tragically, some never recovered. Kelly Johnson wasn't taken by surprise. Although many insisted it was tail flutter, he immediately recognized it as the then little understood phenomenon of compressibility. At 500 miles per hour, localized airflow over certain parts of the aircraft was reaching supersonic velocity, and this produced shock waves and serious problems. The P-38 was the first aircraft to encounter this, and so little was actually known about it that Johnson launched exhaustive wind tunnel studies and an accelerated dive test program headed by Chief Test Pilot Milo Burcham. After more than 2 years, he finally identified the problem as shock stall on the wing, which reduced lift and increased drag, thereby inducing the nose-down tuck. Typically, he was quick to devise a cleverly simple remedy: a dive flap mounted to the main wing spar that, when deployed, generated a positive pressure field, immediately restoring lift and a nose-up pitching moment. Flown on every battlefront, the P-38 excelled in combat. Christened the fork-tailed devil by Germans, the versatile fighter, combining speed and load-carrying capability, proved adaptable to a wide array of combat roles, and its long legs made it ideal for the vast reaches of the Pacific, where it destroyed more enemy aircraft than any other Allied fighter. Impressive though it was, Kelly Johnson was never satisfied with it. He'd long foreseen the inherent limitations of prop-driven aircraft, and though unaware of developments in Germany and England, where turbojets had already been successfully developed, he decided that props had to go. Thus he and Hibbard became the first in this country to seriously pursue the possibilities of turbojet propulsion, when in 1939 they asked Nathan Price to design an experimental turbojet power plant. Design of the L-1000 got underway in 1940, and by 1942, Price had come up with a truly advanced design, a high compression ratio, twin spool, axial flow power plant promising an extraordinary 5,100 pounds of thrust. Meanwhile, Johnson and a young engineer named Willis Hawkins led a design team that came up with the L-133, a truly radical twin-engine stainless steel aircraft featuring thin wings and canard surfaces and projected to achieve 625 miles per hour at 50,000 feet. But surprisingly, when Johnson submitted a proposal for development of the engine and airframe in March 1942, the Army Air Forces showed little interest. Although launched long after his effort, top-secret development of an American turbojet fighter powered by a British Whittle engine was by then already underway. The Bell XP-59A first flew at Muroc Army Air Force Base on California's high desert in October of 1942, but it proved to be underpowered, overweight, and scarcely optimized for jet flight, and early on, the Army Air Forces decided that it wouldn't meet frontline fighter requirements, though Bell didn't yet know this, and the testing continued. On June 10, 1943, a Bell engineer at Muroc reported back that Johnson had been permitted to examine the still top-secret XP-59A, and he wondered what he was up to. Unbeknownst to Bell, the Army Air Force had already asked Lockheed to submit a proposal for a simpler, single-engine jet fighter built around a 3,000-pound thrust Halford H-1 engine, which would be capable of frontline service. Johnson took in a lot that day, but he'd already been wrestling with jet propulsion for nearly 3 years, and he already had a suitable design well in hand. When he made his proposal at Wright Field on June 18th, he made the astounding promise that he'd deliver an aircraft within just 180 days. Getting immediate approval, he was cautioned that the utmost secrecy was required. Lockheed was already swamped in terms of manpower, tooling, and facilities with wartime contracts. But this was a blessing in disguise, an opportunity to implement an idea he'd been pestering Robert Gross about for years. Let him round up a small group of talented people, designers, engineers, and shopmen, put them under one roof where they could all work closely together, and give him complete authority over everything from procurement to flight test. With no other options, Gross said, "Go ahead." Stealing people from around the plant, just 28 engineers, including himself, and 105 shopmen, he also built a small facility out of discarded shipping crates, using a circus tent for a roof. On June 19th, he laid down the principles under which the project would operate. In 1.5 pages, now preserved on old photostats, they formed the basis for how he'd try to operate for the next 30 years. He'd be responsible for all decisions. Paperwork and red tape would be cut to the minimum. Each engineer would be designer, shop contact, parts chaser, and mechanic, and each would remain within a stone's throw of the shop at all times. There'd be but one object: to get a good airplane built on time. The daily log indicates that 2 days later, he laid out the horizontal structure of the organization. No pyramidal, multi-tiered layers of management. Each project engineer and the shop foreman would report directly to him, and in fact, he'd be looking over everyone's shoulder. He wanted information direct from the men doing the work, and if they had questions, they'd get decisions immediately on the spot. He'd promised the airplane in 180 days, as would become his custom. He gave his men 150. The clock started ticking on June 23rd. Forcefully reminded that simplicity is the keynote of good design, the designers jumped into their work. But this was a new kind of operation, and instead of moving from stage to stage, the schedule demanded an extraordinary degree of concurrency. With finished detailed design still many weeks away, the mock-up was started on June 30th and completed by July 17th. By then, milling and fabrication of parts and the construction of jigs to assemble the prototype was already well underway, and by July 31st, the bulkheads were going into the jigs. And section by section, the airframe started coming together. Throughout this period, however, the design process continued. As concurrent wind tunnel tests revealed problems, the wing and the engine air inlets were the biggest headaches. He'd gambled on the wing, a laminar flow airfoil that had never before been tested on an airplane, and of course, nobody had had any experience with inlets. Johnson was willing to accept mistakes on such an accelerated and risky venture, as long as they were reported promptly. Typically, he never asked why, but what are you going to do to fix it? The project was so secret that his group didn't even have a name. The whole setup reminded one of his design engineers, Irv Culver, of the mysterious place where Hairless Joe, one of Al Cap's cartoon characters in Little Abner, ground up skunks, old shoes, and other unsavory ingredients to brew a potent concoction called Kickapoo Joy Juice. So inspired, he answered the phone one day, "Skunk Works, inside man Culver." Though Johnson wasn't amused, his organization suddenly had a name that stuck. Remarkably, The completed aircraft arrived at Muroc on November 14th, just 143 days after startup. But when the engine was run up 3 days later, there was a terrific roar as the inlet ducts collapsed, sending debris into the engine and cracking the impeller. It took 6 weeks to get a new engine, but on January 3rd, 1944, Milo Burcham successfully completed the taxi tests. And 5 days later, in the chill of the morning on January 8th, Johnson, in white coveralls, overcoat, and stocking cap, worked intently with his crew preparing for the first flight, as over 100 Skunk Works employees stood atop a hill looking on. He wanted everyone who'd worked on the airplane they now call Lulu Bell to be on hand. He told Burcham, "Just fly her, Milo. Find out if she's a lady or a witch." At 9:15, he took off. But only 5 minutes later was taxiing back to report that the landing gear hadn't retracted and that the boosted ailerons felt too sensitive. While the gear problem was being fixed, Johnson assured him that the control sensitivity was normal, and at 10 o'clock he took off again, and this time put on a dazzling 20-minute display, attaining a top speed of 490 miles per hour and reporting a roll rate of 360 degrees per second. Back on the ground, he was able to report that Lulu Bell was indeed a lady. The XP-80 ultimately became the first American aircraft to exceed 500 miles per hour, but this was only the beginning. For months, Johnson had been working on a larger, more advanced version with a 4,000-pound thrust General Electric I-40 engine, promising much greater speed. He promised the XP-80A in just 150 days and delivered it in 132. But as Tony LeVere taxied in after the first flight on June 10th, he'd had a few surprises. Center of gravity miscalculations had caused porpoising. A faulty pressurization valve had channeled 325-degree engine bleed air into the cockpit, and malfunctioning flaps had put the airplane into violent rolls. Only his superb flying skills allowed him to bring it back, and Johnson was so grateful he doubled LeVere's bonus, a gesture pointing up the special relationship between them, and indeed between Kelly Johnson and all of his test pilots. Unlike so many of his peers, Johnson both understood and appreciated what his pilots did. He flew with them whenever possible, shared their concerns, always listened, and then acted on their recommendations. The XP-80A's problems were quickly remedied, and it went on to become the prototype for America's first operational jet fighter. Though it wouldn't enter combat in World War II, the P-80 Shooting Star would deliver awesome performance. In January of 1946, for example, Colonel William Council completed the first non-stop transcontinental jet flight, covering 2,450 miles in a record 4 hours and 13 minutes at an average speed of 580 miles per hour. In June of 1947, flying a specially modified P-80R, Colonel Albert Boyd completed 4 runs over a speed course at Muroc, averaging 623 miles per hour, and reclaiming the world speed record for the United States for the first time in 24 years. And over Korea in November of 1950, a shooting star would down a MiG-15 in history's first all-jet combat. And amply confirming Johnson's methods and his insistence on simplicity, the P-80 would give birth to a number of progeny. Shrewdly sensing the need for a jet trainer, Johnson gambled $1 million of Lockheed money on the development of an F-80C airframe into a 2-seat configuration, which after its first flight in March of 1948 was transformed into the classic T-33, an airplane affectionately called the T-Bird, which would serve as the standard jet trainer for legions of student pilots around the world for the next 3 decades. In response to an urgent Air Force requirement for an interim all-weather interceptor, the T-33, in turn, served as the basis for 3 different models of the F-94 Starfire, which filled a critical void, while newer designs specifically tailored for that role remained under development in the early 1950s. Not done yet, the now vintage design would realize its final incarnation as the T-2V1 Sea Star, an advanced, navalized version of the T-33. All of the iterations of the P-80 design were still yet to come, however, as in 1946 he started design work to meet an Air Force requirement for a new penetration escort fighter. Early on, he explored the possibility of applying new concepts, a delta wing, even in-flight variable wing sweep, and then discarded both, some of the more than 60 concepts he'd examine and reject. When the XF-90 finally rolled out, 3 years later, it was the victim of ever-changing and conflicting requirements, from a time to climb of 35,000 feet in 10 minutes to 50,000 in 5, 900-mile range to 1,500, and then back to 600, and finally ground attack capability in a high-speed, high-altitude design. This prompted him to build a brawny airframe, over 30,000 pounds fully loaded, and stressed for over 12 Gs. When Tony LeVere took off on early test flights, he had to use rocket assist because the pair of small 3,000-pound thrust J-34s still lacked afterburning capability. The usual post-flight congratulations and festivities belied the fact that Johnson knew he was facing terrible odds. With the same pair of inadequate engines as their principal rival, the McDonnell XF-88, yet half again as heavy because the 88 hadn't been beefed up for ground attack, Johnson's airplane was bound to suffer performance-wise. It was overweight and underpowered, and even when afterburning was finally added, boosting combined thrust up to more than 8,000 pounds, its top speed in level flight was only 668 miles per hour, slower than existing operational F-86s. It achieved one distinction, however, when in April 1950, LeVere pushed over into a steep dive, and it became the first Lockheed airplane to exceed the speed of sound. With performance no better than the XF-90s, the McDonnell entry won the competition, but neither design went into production. The whole ordeal taught Johnson never again to take on a job unless the requirements were both well-defined and firm. Even though a failure, the XF-90 went on to demonstrate that he certainly knew how to build a rugged airframe, as in April 1952, it survived the first of a series of atomic blasts, suffering only 20 hours worth of repair work. Meanwhile, Johnson was completing work on a much more unconventional airplane. Designed to meet a Navy requirement for a vertical takeoff and landing, or VTOL fighter, the XF-V1 was supposed to claw its way straight up by means of huge contra-rotating props driven by a twin-turbine power plant, providing more power than the airplane's weight. Engine development lagged, however, and after test pilot Herman Fish Salmon first lifted off from the lake bed at what was now called Edwards Air Force Base in December 1953, the underpowered XF-V1 continued to rely on its makeshift landing gear for all takeoffs and landings. Once aloft, however, Salmon was able to demonstrate that it could make satisfactory transitions from horizontal to vertical flight, and that it could hover in the vertical attitude. But, lacking the promised power, and explaining in his words that it's awful hard to fly an airplane looking over your shoulder, Salmon wasn't eager to attempt vertical liftoffs or touchdowns. Neither was Johnson, who, believing a designer shouldn't be afraid to fly his own airplane, had the integrity to recommend cancellation of the whole project. By that time, however, he already had a much more promising design on the ramp at Edwards. When Tony LeVere first saw it, he asked incredulously where the wings were. But those tiny, blade-thin wings and everything else about the XF-104 were actually the product of years of careful thought, effort, and Johnson's determination this time to employ his Skunk Works methods. Back in 1947, he'd modified a P-80 with wingtip-mounted ramjets, and with fish salmon at the controls, it became the first piloted aircraft to fly on ramjet power alone. These tests supported a major Skunk Works type of effort to explore a whole new realm. At a time when missile and guidance system technologies were still in their infancy, Johnson's team had to design a pilotless Mach 3 testbed to further explore ramjet technology. The X-7 was the product of their efforts, and its tiny, thin, slightly tapered wings, Johnson's solution to the problems of high Mach flight, has been thoroughly tested on rockets and with scale models. The X-7 first flew in April 1951 and went on to a remarkable career. Launched from a B-29, boosted to high speed by powerful rockets, and then flying on various ramjets under test, it ultimately exceeded Mach 4 and climbed well above 100,000 feet. Thus those small, thin wings were already more than just a theory when Johnson visited the Korean battlefront in 1951. Still smarting from the XF-90, he'd gone there to talk to the ultimate customers, combat pilots, about what they wanted in a fighter. To a man, it was higher speed, more altitude, and less complexity. Intent on giving them just that, he made an unsolicited proposal to build a fighter for which no requirement yet existed. When he promised Mach 2 and 60,000 feet in a simple, lightweight fighter, Colonel Bruce Holloway stepped into the next room and within 2 hours returned with a short 1.5-page list of requirements. This time, with a firm, straightforward requirement, Johnson returned to his favorite Skunk Works mode of operation, and less than a year later, in February of 1954, Tony LaVere lifted the XF-104 from the lake bed for its first flight. Though configured with a much lower thrust engine than the powerful J-79 scheduled for the production model, the XF-104 was still faster than any other fighter in the world. But Johnson had produced more than just a dazzling performer. Fanatical about costs and producibility, while design of the prototypes was still underway, he'd set up a small group of engineers to find the cheapest and most efficient way to produce each part of the production airplane, an innovation which would result in savings of about $12,000 per aircraft and millions for his customers. When the press finally got to see the F-104, they called it the missile with a man in it, and they weren't far off the mark. The first Mach 2 operational aircraft in the world, it would go on to shatter every significant record on the books. 91,000 feet and 1,400 miles per hour in May of 1958, making it the first aircraft ever to hold both the world altitude and speed marks simultaneously. 3 time-to-climb records later that year. And in 1959, it became the first airplane taking off on its own power ever to climb above 100,000 feet, as Captain Joe Jordan zoomed up over 103,000 feet. This kind of performance clinched the 1958 Collier Trophy for Johnson. While the Starfighter was capturing headlines with record-breaking performances, another, much more exotic Johnson design was unbeknownst to all but a few, almost daily cruising in level flight at altitudes far beyond any official records. It had been born of the massive arms buildup of the early 50s, when U.S. intelligence agencies urgently needed confirmation of reports of major Soviet advances in intercontinental range bombers and ballistic missiles. The decision to proceed with overflights led to a design competition for a reconnaissance aircraft capable of 70,000 feet. Though Lockheed hadn't been invited to participate, Johnson had caught wind of it and hastily submitted a proposal to build the CL-282, essentially a modified F-104 with a wide-span, high-aspect ratio wing. Though it lost out to the Bell X-16, Kelly Johnson wasn't about to quit. Over the years, he'd gotten to know a lot of people in high places, and he developed consummate lobbying skills. With a revised design and promising an airplane within just 8 months, he got the go-ahead to produce 20 aircraft for $22 million. The project, codenamed Aquatone, was directed by the CIA's Richard Bissell, who found the Skunk Works' streamlined, informal method of getting things done much to his liking. Secrecy limited access to a mere handful of CIA and Air Force personnel, which was fine with Johnson because it freed him from a lot of needless paperwork and interference. The urgency of the project also freed him from what he regarded as the tyranny of technical specifications. His customers simply wanted an airplane that could do the job, and all he had to do was deliver on time. While the article, as it was called, was a relatively conventional design, the extreme altitudes at which it was supposed to operate imposed severe demands. Forced to ruthlessly cut weight, he reduced structural components to the minimum and designed delicate, glider-like wings spanning 80 feet and weighing less than 4 pounds per square foot. The fragile airframe was designed around a special high-altitude version of the J-57 engine, virtually hand-built to extremely high tolerances and originally producing 10,500 pounds of thrust. When the disassembled aircraft was unloaded from a C-124 at a remote desert test site in July of 1955, Johnson had met yet another seemingly impossible deadline. After reassembly, it was rolled out into daylight for the first time and painstakingly prepared for its taxi tests. On August 1st, as he had so many times in the past, Tony LeVere climbed into the cockpit. During his third run that day, he suddenly noticed that he was more than 30 feet off the ground. Coming down hard, the tires blew and the brakes failed and caught fire. Reporting afterwards, he explained that at 70 knots, I became aware of being airborne, which left me with utter amazement, as I had no intentions whatsoever of flying. Those fragile wings had more than enough lift. He completed the first real flight 4 days later, and on a subsequent flight reported that the aircraft climbed toward the heavens like a homesick angel. To conceal its true purpose, the Angel was given the misleading official designation U-2, and a cover story was released to the effect that it was being developed as a high-altitude research vehicle for the National Advisory Committee for Aeronautics. While it would perform this role admirably, tests focused on preparing the U-2 for its real mission, to carry 700 pounds of high-resolution camera equipment up to altitudes then beyond any air defense capabilities. And in July 1956, just 11 months after first flight, it commenced its clandestine operational career. Climbing to well above 70,000 feet as fuel burned off, the U-2 successfully completed flights over denied areas and brought back the first hard data on the status of Soviet military preparedness and the true extent of its intercontinental ballistic missile program. Called the Dragon Lady by its pilots because it reminded them of the beautiful, mysterious, and sometimes treacherous character in the Terry and the Pirates cartoon strip, it flew with virtual impunity for 4 years until that day in May of 1960, when Francis Gary Powers was shot down by a surface-to-air missile. While deep penetration of Soviet airspace came to a halt, the U-2 continued to overfly hotspots around the world, such as in 1962, when it confirmed the existence of missile launch sites in Cuba. And it would also continue to perform an incredibly wide array of extremely high-altitude research missions. Kelly Johnson had reason to be proud of his Angel. The Skunk Works had finally been formally established as Lockheed Advanced Development Projects, and on this, its first production program, he'd refunded $2 million from the original $22 million contract and built an additional 5 airplanes out of spare parts. Surely one of the best bargains in defense procurement history. That pride was rekindled when in 1981, the larger, more sophisticated TR-1 was rolled out years after U-2 production had ended. It was the first time the Air Force had ever put an aircraft back into production. And it remains to this day the highest flying single-engine piloted aircraft in the world. Back in December of 1956, the Skunk Works' remarkable performance on the U-2 had convinced Lockheed to give Johnson the job of designing and developing prototypes for a small military jet transport. Dollars were scarce, competition keen, and he'd only have 8 months to do the job. Being on time had always been one of his cardinal rules, and in just 241 days he delivered the Jetstar. He'd actually been working on designs for a large jet transport since 1944. This trim little craft was actually a scaled-down version of the L-193, an innovative 1953 design which the airlines had feared too risky to support. Johnson, who continued to put in long hours as a flight test engineer on this project, was out to prove them wrong. And he was more than pleased with the results. A top speed of over 600 miles per hour, a peak altitude of 52,000 feet, and with wing tanks, a range of over 3,000 miles. The Jetstar easily won the competition, and though only a limited number went into military service as C-140s, ultimately more than 200 were produced, and a great many of them remain in service to this day. The Jetstar was a pleasant diversion as he worked on another, much tougher project. Even as development of the U-2 was still underway, he'd projected that air defenses would catch up with it within 2 years, and he'd initiated a remarkable series of design studies for a liquid hydrogen-fueled supersonic successor capable of climbing above 90,000 feet. Performance varied from Mach 2.5 and a range of 2,200 miles to Mach 4 and 9,000 miles. Because of the extremely low volumetric density of liquid hydrogen, however, the latter speed and range capability could only be achieved by building an airframe twice the size of a B-52. That was far too costly, and thus a much smaller design at the lower end of the performance spectrum went into development as the CL-400 in 1956. Though the CL-400 proved the technical feasibility of a liquid hydrogen-powered aircraft, Johnson was dissatisfied with its short range and convinced that the problems of producing and transporting fuel around the world were insurmountable. Refusing to build an airplane he didn't believe in, he recommended cancellation of the project in 1957. But he had an ace up his sleeve. As concurrent with the liquid hydrogen studies, he'd also examined the potential of another advanced design using jet fuel, which at some loss in altitude promised Mach 3 cruise and 4,000-mile range. It was the genesis of his most spectacular creation. Given approval to proceed, in April of 1958, Johnson began a series of design studies, unveiled publicly here for the first time, for what he initially called the U-3, and then the Archangel, because it would soar much higher than the U-2. He explored various means by which he could get the vehicle to altitudes as high as 150,000 feet, employing a variety, or even a combination of rocket, ramjet, and turbojet power plants. At one point, he looked at the use of balloons to lift it to its rocket boost phase, and then at using a modified U-2 to tow a ramjet vehicle to 60,000 feet for engine ignition. He even considered a multi-staged vehicle, and one with inflatable wings and empennage. And throughout, he was challenged by the urgent need to reduce radar cross-section. For the first time, stealth would have to be designed into the airplane. The intense design gestation process was completed in just 16 months, and when he presented his 12th concept to the CIA and Air Force in August 1959, he got the go-ahead. When the stunningly beautiful A-12 was finally rolled out for its initial tests in April 1962, It wasn't some fantastic, multi-staged aberration. It was an honest airplane, but nothing like it had ever been built before. Ironically codenamed Oxcart and designed for sustained Mach 3.2 cruise at altitudes between 75 and 95,000 feet, it posed by far the greatest challenge of Johnson's career, as everything from structural materials to hydraulic fluid and fuels had to be invented from scratch. For example, because of the intense heat at sustained Mach 3 speeds, averaging more than 550 degrees on the surface of the airplane, Johnson employed a titanium alloy for more than 90% of the airframe. But no one had ever before attempted to process such quantities of the extremely hard metal to the purity and strength levels required. And thus new forging and milling processes had to be invented and perfected. When the thin titanium skin on a wing panel shriveled up during heating tests, Johnson separated the panels from the wing spars with extrusions and put the now famous corrugations in the skin. When heated thereafter, the corrugations merely deepened a few thousandths of an inch and on cooling returned to their original shape, a common-sense solution to a difficult problem. There were literally thousands of such problems to overcome, and as always, Johnson stayed on top of all of them, looking over people's shoulders and asking lots of questions, always the best way, in his view, to get people to solve problems. And he continued to amaze everyone with, for example, on-the-spot predictions of skin temperatures, which after hours of calculation they'd find were within 1 or 2 degrees of the exact figure. The whole effort, completed in absolute secrecy with an incredibly small group of people, was all the more remarkable because it was done without the benefit of computers. As Johnson later recalled,
when you think back to 1958, when the basic design work on the prototypes for this airplane was being designed and built, we had to make use of the Michigan computer, which is a 12-inch slide rule, and it did its job quite well.
All of this prodigious effort was about to come to fruition when on April 25, 1962, preparations for high-speed taxi and an initial brief liftoff were completed. But as Lou Schock sped down the runway, he encountered nose-wheel steering problems and had to kick in heavy right rudder. Then, as Johnson wrote in his log, the aircraft got off the ground, and there was an immediate change of rudder angle. This set up lateral oscillations which were horrible to see. Schock was lucky to get the airplane back on the ground. The problem was fixed post-haste, and the next day he completed the first unofficial flight with the gear down. On April 30th, Johnson was back with an entourage of VIPs for the official first flight. Looking like he didn't have a care in the world, he offered a few last words of encouragement and advice before Schock taxied out. And from there, everything went flawlessly. "59 minutes later, Schock was back on the ground, welcomed by an elated Kelly Johnson and the small, awestruck assembly who just witnessed something very special. Limited by interim J-75 engines, the A-12 didn't begin to realize its full potential until after the Pratt & Whitney J-58s, for which it was designed, finally arrived in January 1963. At 32,500 pounds of thrust, the J-58 was every bit as exotic as the airplane itself. In combination with an extremely complex inlet and exhaust ejector system, it operated as a normal afterburning turbojet up to speeds of about 1,600 miles per hour, and then shifted to bleed bypass cycle, with the inlet actually providing most of the thrust at Mach 3 cruise. When a two-seat trainer became available in early 1963, Johnson, true to his convictions about flying his own aircraft, jumped into the rear cockpit, and, taking control after climb-out, he'd fly supersonic for the first time in his life. During the course of the test program, a pair of airframes were modified for a highly unconventional mission. In 1964, the Skunk Works built a small, 42-foot-long airframe with the very same materials used on the A-12. Designed to overfly areas deemed too risky for air crews, the D-21 drone would ride piggyback atop an A-12 for Mach 3 launches at 80,000 feet, and powered by a ramjet originally developed during the X-7 program, it would be even faster than the A-12. The finished article was mounted to its mothership, now designated M-12, in December 1964. And on December 22nd, the unusual pair taxied for the first time, and flight tests got underway. After takeoff on launch missions, the M-12 climbed to a rendezvous with a KC-135 for refueling, and then proceeded on to the predetermined launch point, where the backseater would monitor the systems and initiate the launch procedures. While there were several successful tests, it was always a very risky business at best, and Kelly Johnson personally canceled this program after a fatal mid-air collision in 1966. By then, however, he already had two other very successful ox cart progeny off the ground. The first was the YF-12A, prototype for a proposed high-speed interceptor. It was this aircraft which went on public display when in 1964, President Lyndon Johnson announced the existence of the A-11. And it subsequently put on a dazzling show, as in May 1965, it claimed no less than 9 world records, including a top speed of more than 2,000 miles per hour and a sustained altitude of over 80,000 feet without in any way taxing its full potential. The YF-12 was equipped with an advanced ASG-18 Doppler radar system and configured to carry 3 AIM-47 missiles internally. Though missiles had never before been launched within the YF-12 speed and altitude regime, the aircraft and its systems scored a reported 90% kill rate, even against drones flying head-on down on the deck at distances of 120 miles and more. The Air Force was impressed enough to order 93 of the big fighters into production for the Air Defense Command, but budgetary constraints ultimately resulted in their cancellation. And shortly thereafter, the A-12 was also removed from service, leaving only the Air Force's SR-71, which took over its reconnaissance mission. Though everything about it and its activities would remain cloaked in a heavy shroud of secrecy, this was the aircraft that everyone came to know as the Blackbird. The solid coat of black paint, which seemed to add to its allure and mystery, actually had a very practical purpose. It reduced skin temperatures by about 75 degrees. Its clean, elegant lines and the smooth contours of its blended wing-body shape give the impression that an artist had sculpted it into a rare work of art. In aircraft design, however, more than any other field, form follows function, and here again, every line, every detail of the airplane exists only to serve some practical purpose. The chines, for example, which extend from the wing to the nose and flow gracefully up into the fuselage, actually satisfied a number of requirements. Aerodynamically, they reduced drag and added lift while also enhancing the stability of the aircraft. The SR-71's mission was long-range reconnaissance, and its fuselage was essentially a big fuel tank, and thus the chines also served to house its sophisticated cameras and sensors. Finally, those sloping contours extending up from the chines enhanced the airplane's survivability by reducing its radar cross-section. Thus, while an artist might envy its striking beauty, an engineer would only marvel at the logical genius of its design. That genius was recognized when, in 1964, Kelly Johnson became the first person ever to be awarded a second Collier Trophy. The SR-71 went on to claim the world absolute speed and altitude records, and then repeatedly extended them. And to the public, it always remained Kelly Johnson's mysterious, record-breaking Blackbird. The crews who flew it, however, had another name for it. Throughout its long operational career, it remained invincible and incredibly effective. And to its crews, it was Habu, dark-skinned pit viper with a deadly bite. And though it was finally retired from Air Force service in 1990, Kelly Johnson's Mach 3 masterpiece is still charting the future, its crews still looking up toward the blue-black void of space, flying exotic research missions for the National Aeronautics and Space Administration. When he retired in 1975, Kelly Johnson had been on the cutting edge of an advance from 200 to more than 2,000 miles per hour. He'd been involved in the design of 44 different airplanes, many of them among the classics of aviation history. And at the time, he was still looking very much into the future. He'd gotten the Skunk Works into a project which would bear fruit in the F-117A, the world's first true stealth aircraft. And he'd left a legacy which would leave its mark on the future. It seems kind of ironic that a lowly creature, known primarily for its odoriferous emanations, had, by the time Kelly retired, become a universal symbol for excellence. What was his secret? Well, he had a remarkable capacity to take a complex problem, reduce it to its simplest components, and then take the most direct and sensible approach to its solution. Always a maverick, he was smart enough and tough enough not to follow the committee rule of conventional wisdom. This gave him remarkable freedom. With that freedom came a tremendous burden of responsibility. Finally, and most important, he understood himself well enough to realize that with a few good people, you can do remarkable things. Kelly Johnson's greatest legacy wasn't just what he did, but the way he did it.
Aviation, the art of aeronautics, began with the dreamers, inventors, and daredevils who dared to defy gravity. The journey of aviation was nurtured by pioneers like the Wright brothers, whose first flight marked a historic milestone. The role of aircrafts in world wars was groundbreaking, dramatically changing warfare strategies. This initiated a technological evolution in aviation, transforming the simplistic wings of a biplane into the thunderous roar of jet engines. Let's journey through the ages of aviation. Behind every great aircraft, there were great minds. These visionaries, like Sir Frank Whittle, the innovator of the turbojet engine, redefined air travel. Then there's Skunk Works' Kelly Johnson, the genius behind the SR-71 Blackbird. His designs combined speed, stealth, and power, crafting machines that dominated the heavens. The contributions of these pioneers have left an indelible mark on the canvas of aviation, shaping the course of history and inspiring generations of engineers and aviators. Each epoch in aviation history gave birth to extraordinary aircrafts, each with their own unique features and roles. The Lockheed SR-71 Blackbird was a marvel of speed and stealth. The F-105 Thunderchief, a supersonic fighter bomber, was vital in the Vietnam War. The P-51 Mustang, a long-range fighter, was critical in World War II. The P-47 Thunderbolt, a heavyweight fighter, was used extensively in the same war. The A-10 Thunderbolt II, the Warthog, is a close air support icon. The Messerschmitt Me-262 marked a leap forward in aviation technology. Each of these game changers were instrumental in their eras, and their legacies still resonate today. Beyond the game changers, there are those that have transcended their practical roles to become icons. The Concorde was not just an aircraft, it was a supersonic symbol of luxury and speed. The B-52 Stratofortress, a strategic bomber, is an icon of power and resilience. These magnificent machines and others like them have become much more than just aircrafts. They are enduring icons that encapsulate the audacious spirit, the relentless innovation, and the boundless ambition that define the world of aviation. For more amazing aerial footage, and to join us in this incredible journey, check out the DroneScapes YouTube channel.
If you enjoyed this video, please remember to like and subscribe. And as always, thank you for watching.